Hello there and welcome to Life Beyond Seen, where the world's quieter and more difficult places are given the time they deserve, explored slowly, carefully, and without any rush toward conclusions that the subject itself would resist. Tonight, we are heading somewhere that most people have never heard of, and yet it is one of the most consequential stretches of ocean on the surface of this planet. A place that does not appear on most people's mental map of dangerous waters, not because it lacks the credentials, but because it has always done its work quietly, away from the shipping lanes that made certain seas famous, away from the dramatic coastlines that gave other waters their reputations, and away from the kind of human traffic that turns a place into a story people tell. Imagine, if you will, a ship, not a large one. Something in the range of 60 metres, built for work rather than comfort, moving through water that is the colour of old pewter, under a sky that offers nothing in the way of reassurance. The horizon, when it is visible at all, is a low grey line that blurs into cloud before it has a chance to become scenery. The water has a particular quality in this part of the world. It is not the deep blue of tropical oceans or the bright cold of the North Sea on a clear winter morning. It is something in between, a grey-green that seems to absorb light rather than reflect it, heavy-looking, thick with cold, moving in long, slow swells that lift the vessel and set it down again with a kind of patient indifference. There is no land visible in any direction. There has not been for some time, and the wind, even on a moderate day, carries a quality that is hard to describe, except to say that it feels purposeful. Like it has come from somewhere specific and is going somewhere specific and does not particularly care that a 60-metre steel vessel is in its way. This is the Irminger Sea. It sits in a part of the North Atlantic that most people, even those who follow weather or oceanography or maritime history, could not immediately place on a map. It occupies a roughly oval basin between the east coast of Greenland and the west coast of Iceland, extending southward toward the Reykjanes Ridge, which is the underwater mountain chain that forms its eastern boundary. At its widest, the Irminger Sea stretches approximately 1,100 kilometres. That is a considerable amount of open water. It is named after the Danish naval officer Carl Ludvig Christian Irminger, who studied these waters in the mid-19th century and was one of the first people to describe the warm current that bears his name. But naming something, as is often the case, does not mean you have tamed it or even fully understood it. The Irminger Sea has been studied, sailed, fished, and surveyed for well over a century, and it continues to resist easy characterization. It is not simply cold. It is not simply stormy. It is not simply remote. It is all of those things at once, and they interact with each other in ways that make the whole more dangerous than any single part would suggest. The surface of the Irminger Sea is rarely still. Swells in this region can exceed 15 metres during winter storms, and the cloud cover is persistent enough that on many days the sky and the water seem to be in conversation with each other, both grey, both low, both pressing in from different directions. Meteorological visibility can drop to near zero in fog or heavy precipitation, and the temperature of the air hovers near or below freezing for much of the year. It is not a place that announces its dangers with theatrical weather in the way that some seas do. It does not always rage. Sometimes it simply sits there, cold and quiet and deeply unwelcoming, and that in some ways is harder to prepare for than a storm you can see coming. Before we go much further, I would love to know where you are listening from tonight. Are you somewhere warm, tucked in with the heating on and rain at the window? Or somewhere cool and still, with the kind of quiet that only comes late at night when the rest of the house has gone to sleep? Maybe you are in a city, with the low hum of traffic somewhere outside, or somewhere rural where the darkness is a little more complete. Whatever the temperature is where you are right now, I can tell you with some confidence that it is almost certainly more comfortable than the surface of the Irminger Sea at this time of year. And I think that contrast is actually part of why this place is worth spending time with tonight. Because the Irminger Sea is not somewhere most of us will ever go, and yet what happens there matters to all of us, in ways that take a little while to explain. If this is the kind of quiet, careful storytelling that you enjoy, I would be genuinely grateful if you took a moment to like this video or subscribe to Life Beyond Seen. It is a small thing that makes a real difference in helping this channel find people who might enjoy spending an evening with a difficult and fascinating place. And now, let us settle in. The Irminger Sea has a way of resisting easy description, and I think that is partly because it does not fit neatly into the categories we tend to use for dangerous or important bodies of water. It is not the North Atlantic in the broad famous sense. It's not the Arctic Ocean. It is not the Labrador Sea, which sits on the other side of Greenland and has a slightly higher profile in oceanographic literature. The Irminger occupies a kind of in-between space, geographically and conceptually, and that in-between quality is actually central to what makes it so interesting and so unforgiving. It is a sea defined by collision. Warm water and cold water meet here. Wet Atlantic air and dry Arctic air meet here. The geography of Greenland and Iceland and the underwater topography of the Reykjanes Ridge all converge to create conditions that are, in the technical language of oceanographers, dynamically complex, which is a polite way of saying that a great many forces are acting on this water at the same time, pulling in different directions, and the result is a place that behaves in ways that are difficult to model, difficult to predict, and difficult to survive if things go wrong. Part of what makes the Irminger Sea difficult to understand is that it does not look, on a map, like a place that should be particularly remarkable. It is a roughly oval patch of ocean between two well-known landmasses. Iceland is a country with airports and hot springs and a tourism industry. Greenland is large and icy and remote, but not unknown. The waters between them should be, you might think, simply cold and windy and navigable with the right equipment. And in a certain narrow sense, that is true. Ships cross the Irminger Sea regularly. Fishing vessels work it year-round. Research ships have been going there for decades. It is not impassable. But surviving the Irminger Sea and understanding it are two different things, and even the people who have spent careers studying it will tell you that the sea has a way of surprising them. The forces at work in this basin, the oceanographic, meteorological and geological forces interact in ways that even modern forecasting and modelling struggle to fully capture. Weather systems develop faster than expected. Currents do things that the models did not predict. The water itself, at depth and at the surface, behaves according to dynamics that are still being worked out by some of the best oceanographers in the world. It is a sea, in other words, that has been known for a long time and understood only partially. And that gap between familiarity and understanding is where most of the danger lives. When sailors first began crossing this water, they had neither the instruments to measure what was happening beneath the surface, nor the meteorological tools to anticipate what the atmosphere was about to do. They had experience, intuition, the stars when the stars were visible, and the accumulated knowledge of people who had made the crossing before them, and they lost ships anyway. Not because they were careless, but because the Irminger Sea has a particular talent for creating conditions that exceed what experience alone can prepare you for. Modern sailors have GPS, satellite weather imagery, ice charts, depth sounders, and communication equipment that would have seemed like magic to a Norse navigator in the 10th century. And they still lose vessels in these waters. Not often, not routinely, but often enough that the sea has a reputation among the fishing communities of Greenland and Iceland that is spoken of with a particular kind of respect, not the dramatic respect you give to something that is obviously theatrically dangerous, the quieter kind, the kind that means you watch the barometer carefully and you do not push your luck. So what is it exactly that makes the Irminger Sea so hard to survive? The answer is not a single thing. It is never a single thing with a place like this. It is a combination of geography, oceanography, meteorology and physics that stack on top of each other in ways that compound the risk at every level. The cold water, the confused seas, the rapid storm development, the remoteness, the depth of the basin, the forces moving beneath the surface, all of these things are present at the same time, and they interact. Understanding the Irminger Sea means understanding each of these layers separately and then understanding how they work together. That is what we are going to do tonight. We are going to take the sea apart carefully, look at each of the forces that shape it, and try to understand why a place that sits between two inhabited land masses, a place that has been navigated for over 1,000 years, continues to be one of the most demanding and dangerous bodies of water on Earth. We will start with the physical geography, because the shape of the seafloor and the position of the surrounding land do more to explain the character of the Irminger Sea than almost anything else. The basin, the ridges, the straits, the coastlines, all of them are not just scenery. They are the architecture of the danger. The seafloor of the Irminger Sea is not flat. That might sound like an obvious thing to say about an ocean basin, but it matters here more than in most places, because the shape of the bottom directly determines how water moves, where currents accelerate, and how the deep and shallow layers of the ocean interact with each other. The central Irminger Basin drops to around 3,000 meters in its deepest sections. That is roughly the height of a significant mountain, inverted sitting beneath the surface of the water. The basin is wide and relatively smooth in its center, but its edges are defined by some of the most geologically significant features in the North Atlantic. To the east, the Reykjanes Ridge forms a long underwater spine running roughly northeast to southwest. This is part of the Mid-Atlantic Ridge System, the same chain of underwater mountains that runs the length of the Atlantic Ocean, where the North American and Eurasian tectonic plates are slowly pulling apart. The Reykjanes Ridge rises steeply from the deep ocean floor, and in places comes within a few hundred meters of the surface. Iceland itself is essentially the most prominent peak of this ridge system, pushed above sea level by a combination of the ridge and a volcanic hotspot beneath it. The ridge does not just mark a geological boundary, it acts as a physical barrier that shapes how water masses move. Currents that encounter it are deflected, deepened, or split, and that deflection has consequences all the way up to the surface. To the north, the Denmark Strait sits between Greenland and Iceland like a narrow corridor. At its shallowest, the strait's sill reaches only about 600 meters deep, which is relatively shallow for a passage connecting two ocean basins. This matters enormously because the Denmark Strait is one of the primary pathways through which cold, dense Arctic water moves southward into the North Atlantic. The shallow sill acts as a kind of gate. Water that is cold enough and dense enough to overflow the sill does so in enormous quantities, and the consequences of that overflow ripple through the entire Irminger Basin. We will come back to the Denmark Strait in more detail later, because what happens there is one of the more remarkable physical processes on the planet. For now, it is enough to know that the strait to the north is constantly feeding cold water southward, and that this flow is one of the defining facts of the Irminger Sea's character. To the west and south, Greenland's east coast curves around toward Cape Farewell, the southernmost point of the world's largest island. Cape Farewell sits at roughly 60 degrees north latitude, which puts it at about the same latitude as Oslo or the southern tip of Alaska. The cape itself is not particularly dramatic in appearance from a distance. It is rocky, often cloud-covered, and surrounded by water that is rarely calm. But its position is crucial. It is the point around which two very different water masses are forced to interact, and it is the point around which some of the most intense wind systems in the North Atlantic are organised. Cape Farewell is not just a geographic landmark, it is a fulcrum around which much of the Irminger Sea's behaviour turns. Now, within this basin, bounded by the ridge to the east, the strait to the north, and Greenland's coast to the west, two fundamentally different bodies of water are in constant contact. The first is cold polar water, which arrives from the north through the Denmark Strait and along Greenland's east coast. This water is cold, relatively fresh compared to open Atlantic water, and dense. It tends to sit in the upper layers of the sea and move southward, carrying with it the thermal signature of the Arctic. The second is the Irminger Current. The Irminger Current is a warm, salty branch of the North Atlantic Current, which is itself the continuation of the Gulf Stream as it crosses the open Atlantic. The The North Atlantic current carries heat from the tropics northeastward toward Europe, and as it does, one of its branches peels off and curves southward around the tip of Iceland, then westward and northward along the southern edge of Greenland. This branch is the Irminger Current, and it brings with it water that is noticeably warmer and saltier than the polar water it encounters. Surface temperatures in the Irminger Current can reach 8 degrees Celsius, or slightly above, which sounds cold, but is dramatically warmer than the 2 or 3 degree water that arrives from the north. The collision of these two water masses is not a gentle mixing. It is a persistent zone of thermal and salinity contrast, a boundary that oceanographers call a frontal zone, and it runs through the Irminger Sea in ways that shift seasonally, but never disappear entirely. On one side of the front, the water is relatively warm and salty. On the other, it is cold and fresher. The boundary between them is sharp enough that a ship can cross it and detect the change in water temperature within a short distance. This kind of sharp thermal gradient is significant not just for the water itself, but for the atmosphere above it. Temperature contrasts at the sea surface drive atmospheric instability. They create differences in air pressure that generate wind. They influence where storms form and how quickly they intensify. The Irminger Current, in other words, does not make the sea safer by bringing warmth. It makes the sea more dynamically active by creating the conditions for rapid and intense atmospheric development. There is something almost counterintuitive about this. You might expect that warmer water in a cold sea would be a moderating influence, a source of stability, and in some contexts that is true. But in the Irminger Sea, the warmth of the Irminger Current is not evenly distributed. It arrives in a narrow band along a specific pathway, and it meets cold polar water along a sharp boundary. The result is not moderation. The result is contrast, and contrast is what drives instability. The atmosphere above a warm ocean surface behaves differently from the atmosphere above a cold one. Air over warm water rises. Air over cold water sinks. Where these two tendencies meet along the frontal zone, the atmospheric dynamics become complicated very quickly. Pressure gradients steepen. Wind shear increases. The conditions for rapid cyclogenesis, the sudden formation and intensification of low-pressure systems, become favourable. This is one of the reasons why storms in the Irminger Sea can develop so quickly and reach such intensity. The Reykjanes Ridge plays its own role in this. As the Irminger Current moves northward along Greenland's west coast, it eventually curves, and some of its water recirculates within the Irminger Basin. The ridge to the east constrains this circulation, preventing easy exchange with the waters to the east of Iceland. The basin becomes, in effect, a semi-enclosed system where water masses are repeatedly brought into contact with each other, repeatedly mixed and separated, and where the thermal and salinity structure of the water column is constantly being rearranged by the competing forces of inflow, outflow, and surface cooling. Surface cooling is particularly important here. In winter, the Irminger Sea loses enormous amounts of heat to the atmosphere. The sea surface temperatures drop, the water becomes denser, and in the right conditions, this dense surface water can sink, initiating a process of deep convection that we will explore in detail later in this story. For now, the important point is that the Irminger Sea is not simply a passive body of water sitting between two land masses. It is an active participant in the exchange of heat and density between the surface ocean and the deep ocean, and between the ocean and the atmosphere. The physical geography of the basin, its depth, its boundaries, its position between the ridge and the strait and the cape, sets the stage for all of this activity. It is worth pausing for a moment on Cape Farewell specifically, because its name carries a kind of quiet weight that feels appropriate. The name in Greenlandic is Nunap Iswa, meaning simply the end of the land. In Danish and in English, the name Farewell has a different resonance, though the origin is probably a straightforward translation from an earlier navigational term rather than a poetic choice. Still, the name has stuck, and when you consider what happens in the waters around it, the farewell quality feels earned. Cape Farewell is where the cold water flowing south along Greenland's east coast meets the warmer water of the Irminger Current coming around from the south. It is where the wind systems that flow off the Greenland ice sheet encounter open ocean and begin to accelerate. It is where ships rounding Greenland from the east enter the Irminger Basin, and where ships leaving the basin encounter the full force of whatever the sea has decided to produce that day. For centuries, mariners have known that rounding Cape Farewell was one of the more demanding passages in the North Atlantic. The Cape does not make things easy. It concentrates them. The depth of the central basin also matters in a less obvious way. 3,000 metres of water has enormous thermal inertia. The deep water of the Irminger Basin is cold, dense, and stable over very long timescales. But the deep circulation is not static. Cold water cascading over the Denmark Strait sill falls down the continental slope and eventually settles into the basin, displacing older water and creating bottom currents that move along the sea floor. These currents are not directly visible at the surface, but they contribute to the overall circulation of the basin in ways that influence where surface water moves and how the water column is structured at different depths. The Irminger Basin is, in this sense, a three-dimensional system, and understanding its surface behaviour requires understanding what is happening at depth. One thing that oceanographers have noted is that the Irminger Current itself is not a simple, steady flow. It varies seasonally and from year to year. In some years, it carries more heat northward. In others, its influence is weaker. These variations affect the thermal structure of the surface water, the position and intensity of the frontal zone, and ultimately the atmospheric conditions above the sea. A year when the Irminger Current is particularly strong may bring slightly warmer surface waters, which sounds beneficial but can actually intensify the atmospheric instability along the front. A year when it is weaker may bring colder, more uniform surface conditions. The sea does not behave the same way twice in exactly the same sequence, and that variability is one of the things that makes it difficult to develop a simple intuitive model of what to expect from it. The Reykjanes Ridge sitting to the east is also volcanically active in places, though the most intense activity is concentrated further north toward Iceland. The ridge generates hydrothermal venting at depth, which contributes small amounts of heat and chemical material to the deep water. This is not a major driver of the Irminger Sea's character, but it is a reminder that the basin sits within a geologically active environment. The seafloor here is not ancient and inert. It is relatively young in geological terms, still being shaped by the slow separation of tectonic plates, and that underlying dynamism is part of the broader context in which the sea exists. What emerges from all of this when you try to hold it together as a single picture is a basin that is defined by convergence. Warm water from the south, cold water from the north, deep water from below, atmospheric forcing from above, the volcanic ridge to the east, the ice-covered continent to the west, the narrow passage of the Denmark Strait funneling Arctic water southward, the Irminger Current looping northward with Atlantic heat. All of these forces converge in a basin that is deep enough to absorb and recirculate them, but bounded enough that they cannot simply disperse. The Irminger Sea is a place where things accumulate. Energy accumulates. Temperature contrast accumulates. The potential for rapid change accumulates. And it is that accumulation, more than any single dramatic feature, that gives the sea its character. For a sailor or a fisherman, understanding the physical geography of the Irminger Sea in this level of detail is not a practical requirement. What matters on the water is the immediate reality, the wind speed, the wave height, the barometric pressure, the temperature of the air and the sea, the distance to the nearest safe harbour. But the physical geography explains why those immediate realities are so often extreme and why they can change so quickly. The basin is set up by its geography and its oceanography to be a place of instability. Not random instability, but structured instability, driven by the collision of water masses and the geometry of the surrounding land and sea floor. When conditions deteriorate in the Irminger Sea, they are not deteriorating randomly. They are responding to forces that have been building according to the logic of the basin's physical structure. The problem is that the timescale on which those forces operate is not always the same as the timescale on which a vessel can respond. This is part of what makes the sea so demanding. The physical geography creates a baseline level of dynamic activity that is always present, always generating the potential for rapid change. And sitting above that, shaping the atmosphere that interacts with this thermally complex sea surface, is a wind system unlike almost anything else in the North Atlantic. The Greenland ice sheet rises to over 3,000 metres above sea level, and when air encounters that wall of ice and rock, it does not simply flow over it. It does something far more complicated and far more dangerous for anything moving on the water below. The Greenland ice sheet is not simply a large piece of frozen water sitting quietly on a continent. It is a topographic feature of extraordinary scale. A dome of ice and compacted snow that covers roughly 1.7 million square kilometres and rises in places to more than 3,200 metres above sea level. From the perspective of the atmosphere, it functions as a wall. A very large, very cold, very solid wall that stretches across the western boundary of the Irminger Sea and refuses to let the air do what air normally prefers to do, which is move around obstacles gradually, spreading out and losing energy as it goes. The ice sheet does not allow that. It is too high, too broad and too abrupt. When the atmosphere encounters it, the results are not gradual. They are concentrated, accelerated, and sometimes violent. The most well documented of these results is something called the Greenland tip jet. To understand how it forms, it helps to picture the airflow approaching Greenland from the west, moving generally eastward across the continent and toward the sea. When that air reaches the southern edge of the ice sheet near Cape Farewell, it has two options. It can try to go over the top of the ice sheet, which requires an enormous amount of energy and only works for the highest altitude flow, or it can deflect around the southern tip, which is what most of the lower level air does. That deflection is not gentle. The air accelerates as it rounds the cape, in the same way that water in a river speeds up when it is forced through a narrow gap. The geometry of the coastline and the shape of the ice sheet work together to concentrate the flow into a narrow band of extremely fast-moving air that shoots out over the Irminger Sea. That band is the tip jet. It is typically only a few hundred kilometres wide, but within it, wind speeds regularly exceed 40 metres per second. To put that in terms that feel a little more concrete, 40 metres per second is roughly 145 kilometres per hour. That is stronger than many land-based hurricanes at the surface level. The tip jet is not a rare event. It is a recurring feature of the Irminger Sea's atmospheric environment, occurring most frequently in winter and autumn, which happen to be exactly the seasons when fishing vessels and research ships are most likely to be working in the area. It can develop relatively quickly, and because it is a narrow band rather than a broad system, it can be difficult to track and predict. A vessel sitting 200 kilometres from the centre of a tip jet event might experience moderate conditions, while one directly beneath it is dealing with winds that make deck work nearly impossible. What makes the tip jet particularly difficult from a forecasting perspective is its scale. It is a mesoscale phenomenon, meaning it operates at a size that falls between the large weather systems that global forecast models handle well and the very small local effects that can be observed directly. For much of the late 20th century, the Greenland tip jet was poorly represented in operational weather models. The grid resolution of those models was simply too coarse to capture a feature that was only a few hundred kilometres wide and highly dependent on the precise shape of the coastline and ice sheet. Research published in the early 2000s, including work by atmospheric scientists at the University of Reading and the National Centre for Atmospheric Research, helped to formally characterise the tip jet and quantify its intensity. Before that, it was something mariners and fishermen knew existed in a practical sense, because they had experienced it, but it was not well captured by the forecast products they relied on. That gap between what the sea was doing and what the forecast said it would do has cost people their lives. The tip jet is not the only wind system that defines the Irminger Sea's atmospheric character. Running alongside it, and in some ways equally important, are what meteorologists call barrier winds. These form through a different mechanism, Cold, dense air from the Arctic flows southward along Greenland's east coast, and as it encounters the ice sheet's coastal topography, it is deflected and channeled. The ice sheet acts as a barrier, as the name suggests, preventing the cold air from moving inland. Instead, that air is forced to flow along the coast, parallel to the ice sheet, and it accelerates as it does so. When it reaches the southern end of Greenland and pours out into the open Irminger Sea, it brings with it a mass of cold, dense air that interacts with the warmer sea surface below. The interaction between barrier winds and the Irminger Sea's surface is not straightforward. Cold, dry air moving over a relatively warmer ocean surface draws heat and moisture upward rapidly. This destabilizes the lower atmosphere, creating conditions favourable for the rapid development of convective weather systems. These are not the slow-moving frontal systems that meteorologists can track for days before they arrive. They're fast-developing, often localised systems that can intensify over a period of hours. A ship's crew that woke to a manageable morning might find themselves in genuinely dangerous conditions by early afternoon, not because they failed to pay attention, but because the system that produced those conditions developed faster than any forecast had indicated it would. There is a specific type of storm that emerges from this environment, sometimes referred to as a polar low. Polar lows are small, intense cyclones that form over cold ocean waters when cold air masses interact with the relatively warmer sea surface. They are sometimes compared to miniature hurricanes, though the comparison is imperfect. They typically have a diameter of between 200 and 1,000 kilometers, they develop quickly, and they can produce wind speeds in the severe gale to storm range, along with heavy snow and rapidly building seas. The Irminger Sea and the waters around Iceland and the Norwegian Sea are among the most active polar low regions in the world. These storms are difficult to forecast even with modern tools, partly because of their rapid development and partly because of the sparse observational network in the area. Weather buoys exist, but they are widely spaced. Satellite data helps, but polar lows can intensify in the gap between satellite passes. Research vessels sometimes provide valuable data, but they are not always present, and when conditions deteriorate, they may be hove to and unable to provide reliable observations. The combination of the tip jet, barrier winds, and polar low activity creates something that goes beyond a collection of individual hazards. It creates an environment where the atmosphere over the Irminger Sea is structurally prone to rapid, unpredictable intensification. The thermal contrast between the cold air masses coming off Greenland and the warmer, moister air over the Irminger Current's influence zone provides a constant energy source for storm development. The geometry of the coastline and ice sheet focuses and accelerates that energy into specific corridors. The result is a sea where the weather is not simply variable, but where the rate of change itself can be extreme. Meteorologists sometimes use the phrase explosive cyclogenesis to describe situations where a storm's central pressure drops by 24 millibars or more in 24 hours. The Irminger Sea and the broader North Atlantic region experience explosive cyclogenesis more frequently than almost any other ocean basin on Earth. The term sounds dramatic because it is. A pressure drop of that magnitude in that time frame represents a storm intensifying from manageable to dangerous within a single day, sometimes within a single watch. For the people on the water, all of this translates into a particular kind of situational awareness that has to be maintained constantly. Experienced mariners in this region develop a habit of checking the barometer frequently, not just once or twice a day, but every few hours, because a pressure fall that might be unremarkable in a more stable environment can be the first signal of an explosive development in the Irminger Sea. They watch the cloud formations carefully. They pay attention to the feel of the swell, because sometimes the sea registers an approaching storm before the wind does. Swell can travel ahead of a storm system, arriving from a direction that does not yet match the local wind, and a sudden change in swell direction or period can indicate that something significant is building over the horizon. These are skills that come from time on the water, and they are not easily replaced by any single technology. Weather forecasting has improved enormously over the past few decades, and the Irminger Sea has benefited from that improvement. Modern ensemble forecast systems, higher resolution models, improved satellite data, and better understanding of the tip jet and barrier wind dynamics have all contributed to more accurate predictions. But the improvement is relative. The Irminger Sea remains one of the more challenging forecast environments in the North Atlantic, partly because of the mesoscale features that still push the limits of operational model resolution, and partly because the observational network in the area remains sparse compared to what would be needed for truly reliable short-range forecasts. A research paper published in the Journal of Geophysical Research in 2014 noted that even high-resolution regional models showed significant errors in representing tip-jet events, particularly in capturing the precise timing and intensity of peak winds. That kind of uncertainty, even at the level of research-grade modelling, gives some sense of how difficult the practical forecasting problem remains. There is also something worth noting about the way these wind systems interact with the sea's thermal structure. The tip jet and barrier winds do not just create dangerous conditions at the surface, they drive a process called ocean heat loss, in which the cold, fast-moving air strips heat from the sea surface at a rate that can be extraordinary. During intense tip jet events, the ocean heat loss in the Irminger Sea can reach values among the highest recorded anywhere in the world's oceans. This heat loss is not just a weather phenomenon. It has consequences for the ocean's physical structure, cooling the surface water, increasing its density, and setting in motion the deep convection processes that make the Irminger Sea one of the most important sites for deep water formation in the North Atlantic. The weather and the ocean are not separate systems here. They are coupled, each driving changes in the other, and understanding one requires understanding both. This coupling is part of what makes the Irminger Sea so scientifically interesting and so physically demanding. The wind systems that make the surface dangerous are also the wind systems that drive some of the most important oceanographic processes in the North Atlantic. The tip jet that can put a vessel in danger is also the tip jet that, in winter, strips enough heat from the surface to trigger the sinking of cold, dense water to depths of 1,000 meters or more. The same atmospheric violence that makes the sea hard to work in is, in a very real sense, part of what keeps the ocean's global circulation functioning. There is a kind of grim elegance in that, though it is not the sort of elegance that offers much comfort to someone on deck in a Force 10. What the wind systems of the Irminger Sea produce taken together is an atmosphere that operates on its own terms. It is not simply responding to the large-scale weather patterns that move across the North Atlantic from west to east in predictable sequences. It is generating its own disturbances, its own accelerations, its own rapid developments, shaped by the geometry of the ice sheet and the thermal contrasts of the ocean surface beneath it. A mariner crossing the North Atlantic who passes through the Irminger Sea is not just moving through a cold and remote stretch of water. They're moving through a region where the atmosphere has its own internal logic, one that does not always align with what the forecast said 6 hours ago, and one that can shift faster than a crew can fully prepare for. The sea creates its own weather, in other words, and that weather does not wait for anyone. It develops when the conditions are right, which in the Irminger Sea is more often than most places, and it intensifies at a pace that the surrounding geography makes possible, and the sparse observational network makes difficult to track in real time. Understanding that the Irminger Sea is not just subject to bad weather, but is an active participant in generating it, changes how you think about what it means to be out there. The danger is not incidental to the location, it is structural, it is built into the relationship between the ice sheet, the ocean, and the atmosphere in a way that has been operating for thousands of years, and will continue to operate regardless of what any forecast model says. And if the atmosphere above the Irminger Sea is already this complex, this prone to rapid and concentrated violence, then what the sea itself does with all of that energy is the next part of the story. Because the wind does not just move air, it moves water. And the water in the Irminger Sea does not respond to that energy in a simple or orderly way. When the wind moves across water, the water moves back. That is the basic exchange, and it sounds simple enough. But what the wind does to the Irminger Sea, and what the Irminger Sea does in response, is far from simple. The surface of this sea under the influence of the tip jet and barrier winds does not just become rough, in the way that most rough seas are rough. It becomes something more complicated and, in practical terms, considerably more dangerous. The key word is confused. Sailors and oceanographers use that word in a specific technical sense, and it is worth taking a moment with it. A confused sea is not simply a rough sea. It is a sea in which wave energy is arriving from multiple directions at the same time, creating a surface that has no dominant pattern, no orderly sequence of crests and troughs, no rhythm that a vessel can work with. The waves cross each other, combine, cancel, and occasionally stack. The result is a surface that looks from above almost chaotic, a field of peaks and hollows with no clear organisation. In the Irminger Sea, confused seas develop partly because of the geography. The tip jet drives energy from one direction. The barrier winds push from another. Swell arriving from distant North Atlantic storm systems adds a third component. And because the sea is roughly oval-shaped, bounded by Greenland to the west and the Reykjanes Ridge to the east, wave energy can reflect off those boundaries and return into the basin. What you end up with, during a significant weather event, is a surface where swells are arriving simultaneously from the west, the northwest, the south, and sometimes the east, each with its own period and height, all of them interacting in ways that are difficult to model and impossible to predict wave by wave. This matters enormously for anyone on a vessel. There is a common assumption that the danger of a rough sea scales directly with wave height, that a 10-metre swell is simply twice as dangerous as a 5-metre swell. But experienced mariners will tell you that this is not quite right. A vessel can often handle a high but regular swell better than a lower but confused sea. When waves arrive in a consistent sequence, a ship's motion becomes somewhat predictable. The hull rises, pitches, rolls and recovers in a pattern that the crew can anticipate and work around. Cargo can be secured, crew can brace. The helmsman can position the bow to meet each wave at the best angle. In a confused sea, none of that is possible. Waves arrive from unexpected directions. A vessel that has just recovered from a roll to starboard may immediately be struck by a cross swell from the port bow before it has fully righted. The motion becomes violent and unpredictable. Cargo shifts. Equipment breaks loose. People fall. The helmsman cannot keep the bow optimally oriented because there is no single optimal orientation. Every decision about heading is a compromise between multiple threats arriving from multiple angles. 6-metre cross seas can be more damaging to a vessel and more dangerous to a crew than 10-metre seas running in a single clean direction. The Irminger Sea during its worst episodes produces both high swells and confused cross seas layered on top of each other, which is a combination that leaves very little margin. There is another element of the wave environment in the Irminger Sea that deserves careful attention, and that is the question of rogue waves. The term has become somewhat loosely used in popular culture, but it has a specific technical meaning. A rogue wave, also called a freak wave or an extreme wave, is generally defined as a wave that exceeds twice the significant wave height of the surrounding sea. The significant wave height is itself a statistical measure, roughly the average height of the highest 1/3 of waves in a given sea state. So if the significant wave height is 6 metres, a rogue wave would be 12 metres or more. These are not theoretical events. They have been documented by instruments, captured on radar, and have caused damage to vessels that should have been able to handle the surrounding sea state. For a long time, rogue waves were treated with some skepticism by oceanographers. The mathematical models of wave behaviour suggested that waves of that extreme magnitude should be extraordinarily rare, so rare as to be almost irrelevant for practical purposes. But field data, particularly from the late 20th century onward, began to suggest that rogue waves occur significantly more often than the standard models predicted. The Draupner wave, recorded on a North Sea oil platform on New Year's Day 1995, with a height of around 25 metres in a sea state, with a significant wave height of about 12 metres, was one of the first instrumentally verified examples. Since then, satellite data has confirmed that extreme waves occur across the world's oceans, with a frequency that the classical models underestimated. The Irminger Sea is one of the regions where the conditions for rogue wave formation are particularly favourable. The convergence of multiple current systems, the interaction of the Irminger Current with the cold polar water flowing south through the Denmark Strait, and the complex wave field created by competing wind systems all contribute to an environment where wave energy can focus and amplify in localised areas. When currents oppose the direction of wave travel, wave energy compresses and wave heights increase. When wave trains from different directions arrive in phase, that is, when their crests align, they can combine into a single wave that is far larger than either component alone. The Irminger Sea, with its multiple overlapping wave systems and its strong irregular currents, provides the ingredients for this kind of amplification more reliably than most places. It is worth being clear that rogue waves in the Irminger Sea have not been as extensively documented as in some other regions, partly because the observational network is sparse, and partly because vessels that encounter extreme waves in remote waters do not always survive to report them in detail. But the physical conditions are consistent with elevated risk, and the historical record of vessel losses in the region includes cases where the reported sea state should not, in theory, have been sufficient to cause catastrophic damage. One explanation that has been considered in some of those cases is the encounter with an extreme wave event that was not captured by the available wave observations. What makes all of this more immediate, more consequential in a human sense, is the temperature of the water. The Irminger Sea is cold in a way that has direct physiological consequences. Sea surface temperatures in the region typically range from around 2 degrees Celsius in winter to about 8 degrees in summer, with the colder values concentrated in the northern parts of the basin near the Denmark Strait and along the Greenland coast where cold polar water is most present. 2 degrees is not far above freezing. It is cold enough that the water feels like a physical shock on contact, and that shock is not just uncomfortable. It is dangerous in a precise, measurable way. Cold water immersion triggers a physiological response called cold shock, which occurs in the first 30 seconds to 3 minutes after entry. The sudden cooling of the skin causes an involuntary gasp reflex, which can lead to water inhalation if the person's head is submerged at that moment. The heart rate accelerates sharply, blood pressure spikes, and there is a risk of cardiac arrhythmia, particularly in people with underlying cardiovascular conditions. Even in otherwise healthy individuals, the initial cold shock response can cause panic, disorientation, and loss of breath control that makes it difficult to keep the head above water. In a confused sea with breaking waves, those first seconds are critical. If a person survives the cold shock phase, the next threat is swimming failure. As the muscles cool, their ability to generate force diminishes rapidly. In water at 2 degrees Celsius, useful swimming ability can be lost within 3 to 5 minutes. The hands lose dexterity first, making it impossible to grip a line, operate a signalling device, or pull on a rescue ring. The arms and legs follow. A person who was swimming purposefully a few minutes earlier may find themselves unable to keep their face above the surface, not because they have given up, but because the muscles simply no longer respond adequately to the signals the brain is sending. This is not weakness or failure of will. It is straightforward physiology, and it happens faster in 2-degree water than most people expect. After swimming, failure comes the longer process of hypothermia, the core body temperature dropping below the level at which normal physiological function can be maintained. In water at 2 degrees, the expected time to unconsciousness from hypothermia is roughly 30 minutes to an hour for an average adult without thermal protection. With a survival suit, the immersion suits that are standard equipment on commercial fishing vessels, that window extends significantly, potentially to several hours. But the suit must be donned before entering the water, which in a rapid capsize or catastrophic flooding event is not always possible. And even with a suit, the person in the water is dependent on rescue arriving within a time frame that the Irminger Sea's remoteness makes genuinely difficult to guarantee. The survival window matters because it defines what rescue means in practical terms. If a vessel capsizes in the central Irminger Sea, the nearest search and rescue assets may be hours away by air. Helicopters based in Iceland or operating from Greenland face transit times that can approach or exceed 6 hours to the most remote parts of the basin, depending on weather and the specific location of the incident. In 2-degree water without a suit, 6 hours is not a survival window. It is not even close. Even with a suit, the margin is narrow, and it depends on the person remaining conscious, maintaining their position, and being located in a sea state that allows a helicopter to conduct a safe recovery, none of which can be assumed. There is something almost clinical about laying this out in sequence, and it feels important to pause on that for a moment. These are not abstract statistics. They describe what happens to a person's body in water that covers a significant portion of the North Atlantic, water that fishing crews, researchers and sailors work above every day. The numbers, 2 degrees, 3 minutes, 30 minutes, 6 hours, are the coordinates of a situation that leaves very little room for error and almost no room for delay. The sea does not offer a grace period. It does not wait for the rescue helicopter to arrive. It simply continues to do what cold water does. The combination of confused seas, rogue wave risk, and near-freezing temperatures creates a threat environment that is unusual in its layering. Most dangerous maritime environments present one primary hazard at elevated intensity: extreme wave heights, extreme cold, extreme remoteness. The Irminger Sea presents all of them simultaneously, and they interact in ways that compound the risk rather than simply adding to it. High waves increase the likelihood of immersion. Confused seas increase the likelihood of capsize and make it harder for survivors to maintain position at the surface. Cold water reduces the time available for rescue. Remoteness reduces the probability of rescue arriving within that window. Each factor makes the others worse. Modern vessels working the Irminger Sea are built and equipped to manage this environment. Stability requirements for fishing vessels operating in North Atlantic waters have become significantly more stringent following a series of disasters in the latter half of the 20th century, and the implementation of stability monitoring systems, improved hull designs, and mandatory survival suit requirements has reduced the casualty rate compared to earlier eras. Satellite communication and emergency position indicating radio beacons mean that a vessel in distress can transmit its location automatically, which was not always the case for fishing fleets working these waters in the mid-20th century. But the sea has not changed. The water temperature is the same as it was when Norse sailors crossed these latitudes 1,000 years ago. The wave dynamics produced by the tip jet and barrier winds operate by the same physics they always have. The rogue wave risk is not a new phenomenon. What has changed is the equipment, the communication, and the regulatory framework surrounding the people who work here. The underlying physical environment remains as demanding as it has ever been, and on a bad day in the central Irminger, the gap between modern equipment and genuine safety can close faster than anyone would like. What the surface of the Irminger Sea does then is not simply create difficult working conditions. It creates a situation in which the margin for error is structurally narrow, in which multiple simultaneous hazards interact to reduce that margin further, and in which the consequences of any failure, mechanical, navigational, or human, can escalate rapidly and irreversibly. The sea does not announce its worst moments in advance. The confused swell does not announce itself. The rogue wave does not announce itself. The cold shock does not announce itself. They arrive, and then the clock starts. And beneath all of that surface violence, beneath the confused wave field and the spray and the wind, something else is happening. Something that cannot be seen from the deck of a vessel, that cannot be felt through the hull, that operates on a scale and at a depth that makes the surface conditions look almost incidental by comparison. The Irminger Sea is not just dangerous at the surface, it is active at depths that most people never think about, driven by forces that connect this remote basin to the functioning of the global ocean. To understand why the sea matters beyond its own borders, you have to go down, a long way down, and follow the water that is moving in the dark. There is a place between Iceland and Greenland where the seafloor rises up toward the surface in a long underwater ridge, like a sill across the bottom of a doorway. The Denmark Strait sits above it, a narrow passage roughly 300 kilometres wide at its tightest point, and it is one of the most consequential geographic features in the entire Atlantic Ocean. Not because of what happens at the surface, though the surface is difficult enough, but because of what happens below it, in the dark, where the water is moving in ways that most people never think to imagine. The sill itself sits at around 600 metres depth. That is not especially deep by ocean standards, but what matters is what sits on either side of it. To the north, in the Arctic Ocean and the Nordic seas, water has been cooling for a long time. Cold water is dense water is heavy water, and heavy water, given any kind of slope to follow, will move downhill. The sill of the Denmark Strait is that slope's edge. When the dense Arctic water reaches it, there is nowhere to go but over and down. What follows is one of the largest waterfalls on Earth. Not a waterfall in the sense of white cascading water falling through open air. There is no open air here, only darkness and immense pressure. But the physics are the same. Cold, dense water spills over the sill and plunges down the continental slope on the southern side, descending from around 600 metres to depths exceeding 3,500 metres. The descent is steep, and the flow is enormous. Scientists measuring the Denmark Strait Cataract, which is what it is formally called, have estimated the flow rate at approximately 5 million cubic metres per second. To put that in perspective, all the rivers on Earth combined move roughly 1 million cubic metres of water per second into the oceans. The Denmark Strait overflow is moving 5 times that volume continuously through a single underwater passage in the dark. It is one of those facts that takes a moment to settle. You can picture a river, you can picture a waterfall. But 5 million cubic metres per second, invisible, happening beneath the surface of the North Atlantic, is a different category of scale entirely. It is the kind of thing that makes the word large feel inadequate. As this cold, dense water plunges down the slope, it does not simply fall cleanly and stop. It entrains water around it, pulling warmer, lighter water into the descending flow and mixing as it goes. It generates turbulence at the bottom of the slope that is powerful enough to scour the seafloor, to move sediment, to create features in the deep ocean landscape that can be measured and mapped by research vessels dragging instruments along the bottom. The descending water eventually spreads out across the floor of the Irminger Basin, filling the deepest parts of the basin with cold, oxygen-rich water that has come directly from the surface of the Arctic seas. This process has a name. It is called deep water formation, or more specifically in this context, it is part of the mechanism that produces North Atlantic deep water, one of the primary water masses of the global deep ocean, and it is connected to something that oceanographers spend a great deal of time thinking about, measuring, and in recent years, worrying about. The Atlantic Meridional Overturning Circulation, which is usually shortened to AMOC, is the large-scale system of ocean currents that carries warm surface water northward from the tropics and returns cold, deep water southward. The Denmark Strait overflow is one of its engines. Without the overflow, without that constant plunge of cold, dense water into the deep Irminger Basin and beyond, the circulation would lose one of its primary driving forces. The way AMOC works is sometimes compared to a conveyor belt, though oceanographers tend to wince at that comparison, because it simplifies something that is genuinely complex and three-dimensional. But the basic idea holds. Warm water flows north near the surface, releases its heat to the atmosphere over the North Atlantic, which is part of why Western Europe has a milder climate than its latitude would otherwise suggest, and then cools, becomes dense, and sinks. The sinking is what pulls more warm water northward to replace it. The Denmark Strait overflow is one of the places where that sinking happens, and the Irminger Basin is the receiving vessel for much of that descending water. What this means for the Irminger Sea specifically is that the basin is not a passive container. It is an active participant in a circulation system that spans the entire Atlantic and connects to every other ocean on the planet. The water that sinks here does not stay here. It moves southward along the deep western boundary of the Atlantic, eventually spreading into the South Atlantic and beyond, carrying its chemical signature, its temperature, its salinity, its dissolved oxygen, into waters thousands of kilometers away. Scientists can identify North Atlantic deep water in the South Atlantic, in the Indian Ocean, in the deep Pacific. It has travelled there from places like this, from the Irminger Basin, from the cold, dark water that spilled over the Denmark Strait sill and fell. The bottom currents generated by this process are not gentle. The descending overflow water moves along the seafloor with enough force to affect the sedimentary record of the basin. Geologists studying sediment cores from the Irminger Basin can read the history of overflow intensity in the layers of material deposited over thousands of years. Stronger overflow leaves a different sedimentary signature than weaker overflow. The record goes back through ice ages and warm periods, through climate shifts that reorganised the ocean circulation and changed the face of the planet. The Denmark Strait overflow has been doing this for a very long time, and the Irminger Basin has been recording it the entire time. For a ship sitting on the surface of the Irminger Sea, none of this is directly visible. The crew of a fishing trawler working the Irminger does not feel the overflow happening beneath them. The research scientist on a survey vessel measuring surface conditions cannot look over the side and see the deep water forming below. The connection between the surface and the deep is real and important, but it is not obvious. It requires instruments, patience, and a willingness to think across scales that don't naturally fit human intuition. But the connection is there, and it works in both directions. The deep water formation process affects the surface in ways that are subtle but real. When cold, dense surface water sinks in large volumes during winter convection events, a process that the Irminger Sea is now understood to drive significantly, something researchers confirmed more clearly in the 2000s and 2010s, it creates upwelling of deeper water to replace what has descended. That upwelling brings nutrients from depth toward the surface, which feeds the biological productivity of the sea. The Irminger Sea's fisheries, the halibut, the redfish, the shrimp, exist in part because of the nutrient cycling driven by this vertical movement of water. The overflow and the convection that it helps drive are not just physical and chemical phenomena. They are the foundation of the ecosystem that fishing communities across Iceland, Greenland and the Faroe Islands depend on. There is also the question of what the overflow does to the surface currents. The Irminger Current, the warm, salty branch of the North Atlantic Current that loops around Cape Farewell and runs northward along Greenland's coast, is partly sustained by the circulation that the overflow helps drive. The warm water coming in and the cold water going out are two sides of the same system. Disrupt one and you affect the other. This is why oceanographers monitoring the overflow take it seriously as a climate indicator, not just as a local oceanographic phenomenon. Measuring the overflow is not straightforward. The Denmark Strait is a difficult place to deploy instruments. Currents are strong, storms are frequent, and the seafloor topography creates complex flow patterns that make simple point measurements misleading. Research vessels have been working the strait for decades, deploying mooring arrays, strings of instruments anchored to the seafloor and rising through the water column, to measure temperature, salinity, and current velocity over time. Some of these moorings have been lost to the very currents they were trying to measure. Others have been recovered with data gaps caused by instrument failure or fouling. Building a continuous, reliable record of overflow intensity across the Denmark Strait has taken the combined effort of multiple national research programs over many years, and the record still has gaps. What the available data shows is that the overflow is not constant. It varies on timescales ranging from days to decades. There are periods of stronger flow and weaker flow, driven by atmospheric pressure patterns, wind stress, and the density contrast between the Arctic and Atlantic water masses. In recent decades, as the climate has warmed and the Greenland ice sheet has begun losing mass at accelerating rates, scientists have been watching the overflow carefully for signs of change. Fresh water from melting ice dilutes the surface water of the Nordic seas, reducing its salinity and therefore its density. Less dense water is less likely to sink. If the density contrast across the Denmark Strait decreases, the overflow may weaken. If the overflow weakens, the circulation it helps drive slows. The implications of that extend well beyond the Irminger Sea. There is something almost counterintuitive about the whole picture, and it is worth sitting with for a moment. This sea, this grey, cold, difficult basin that sits between Greenland and Iceland and generates storms faster than forecasting models can track, is not just a hazard to be navigated. It is performing essential work. The overflow plunging down the continental slope, the deep water spreading across the basin floor, the convection overturning the water column in winter. These are not incidental features of a remote and inhospitable place. They are mechanisms that the global ocean depends on. The Irminger Sea is hard to survive in part because it is so physically active, and it is so physically active because it is doing something important. The forces operating 3,000 metres below the surface cannot be seen from the deck of a vessel. A fishing crew riding out a storm in the central Irminger Basin has no direct awareness of the overflow happening beneath them, no sense of the bottom currents moving across the seafloor, no perception of the water column overturning in winter to depths of 1,000 metres. The surface and the deep are connected by physics, but they are experienced separately. The sailor feels the wave, the oceanographer measures the current. Neither one can fully see what the other is dealing with, and yet the two are not truly separate. The deep water formation that happens here shapes the nutrient availability that sustains the fish. The circulation that the overflow drives influences the storm tracks that affect the weather. The warm water brought in by the Irminger current, itself a product of the larger circulation, moderates what the surface temperatures would otherwise be. The sea is a system, and its surface behaviour and its deep behaviour are expressions of the same underlying physics, operating at different scales and different speeds, but connected throughout. What makes the Irminger Sea unusual is that these connections are more direct and more intense here than in most other parts of the ocean. The overflow is large, the convection is deep, the currents are strong, the thermal contrast between incoming Atlantic water and outgoing Arctic water is sharp. Everything is turned up. The result is a sea that is not just cold and remote and stormy, but genuinely, structurally active in a way that produces effects at the surface that no one on that surface can fully anticipate. The confused seas are partly a product of the wind systems. They are also partly a product of the current interactions that the overflow and the circulation drive. The rogue wave risk is elevated in part because of the convergence of current systems that the larger circulation creates. The surface and the deep are not separate problems. They are the same problem, expressed at different depths, all of which means that the Irminger Sea's difficulty is not incidental. It is not just a function of latitude or geography or bad luck. It is a product of the sea being one of the most oceanographically active basins in the Atlantic, a place where the deep ocean is being made, where the global circulation is being driven, and where the energy involved in those processes finds its way to the surface in forms that are genuinely difficult to survive. The overflow will continue whether anyone is watching or not. The cold water will spill over the sill, plunge down the slope, and spread across the basin floor as it has been doing for thousands of years. The question that researchers are now asking, carefully with the data they have and the models they are building, is whether it will continue at the same rate, or whether the changes already underway in the Arctic and on the Greenland ice sheet will alter the balance that makes this process work. That question has answers that extend far beyond the Irminger Sea itself. into the climate of the entire North Atlantic and beyond. But the Irminger Basin is where some of the most important evidence for answering it is being gathered, in conditions that make gathering evidence difficult, by people and instruments working in one of the most demanding ocean environments on Earth. The sea keeps its deepest processes largely to itself, but humans have been trying to understand them and to cross this water for a very long time. The history of that effort, the Norse sailors who came first, the fishing fleets that followed, the researchers who came after them, runs alongside the oceanography and the meteorology as a third thread in the Irminger Sea story. And it begins more than 1,000 years ago, with ships made of wood and people who had no choice but to trust the water beneath them. The Norse sailors who first crossed the Irminger Sea did not have a name for it. They had a direction and a distance, and if the weather allowed, a horizon. Eric the Red made the passage from Iceland to Greenland around 985 CE, leading a small fleet of settlers toward a coast he had already seen once, and been expelled from Iceland for reasons that had nothing to do with the sea. The sagas describe the crossing in the way that people describe things that were survivable, but not pleasant. Ships were lost. Crews arrived exhausted. Some landings were missed entirely, the coast sliding past in fog or the navigation going slightly wrong in the way that navigation goes wrong when your instruments are the sun, the stars, and accumulated experience, and the sky has been overcast for 4 days. Medieval Norse navigation was genuinely impressive for what it could do. Sun compasses, circular discs with a gnomon that cast a shadow to indicate direction relative to the sun, have been found archaeologically, including a fragment recovered from a Norse site in Greenland in 1948. Sailors could also use the stars, the behaviour of seabirds, wave patterns, and the colour and temperature of the water to orient themselves. A skilled Norse navigator could make long ocean passages with reasonable accuracy. The problem with the Irminger Sea is that it regularly removes most of those tools. Cloud cover is persistent. The sun disappears for days at a time. Seabirds are present, but not necessarily directional in the way that land-seeking birds are near a coast. The wave patterns are confused rather than orderly. The water is cold everywhere. What the Norse sailor was left with, in the worst conditions, was dead reckoning. Estimating position based on known speed, heading and time elapsed, and the knowledge that Greenland was roughly to the west, and that if they kept going, they would eventually find it, or not. The sagas are not technical documents. They do not record wave heights or wind speeds, but they carry a tone when describing this particular crossing that is distinct from descriptions of other passages. The Irminger Sea portion of the Iceland to Greenland route appears in the literature as something to be gotten through, rather than something to be navigated. The word that recurs in various forms is endurance. You held on, you kept going, you arrived, or you did not. Eric the Red's initial settlement voyage apparently lost several ships. The Landnámabók, one of the Icelandic sagas that records the settlement of Iceland, and by extension some of the Greenland voyages, suggests that of the 25 ships that set out in the colonising expedition, only 14 arrived. The others turned back or were lost. Whether those losses occurred in the Irminger Sea specifically or elsewhere along the route is not always clear, but the Irminger crossing was the most exposed and most dangerous portion of the passage. The waters around Iceland and along the Greenland coast offered their own hazards, but the open stretch between them, roughly 400 kilometres of deep water with no shelter and no intermediate landfall, was where the sea had the most room to work on a wooden ship. What is striking, looking back at this from a distance of 1,000 years, is how casually the Norse incorporated these losses into their planning. They expected to lose ships. They brought enough people and enough vessels that losing some was survivable as a collective enterprise, if not for the individuals involved. The Irminger Sea was a cost of doing business. It was not a deterrent. The Norse continued making the crossing for generations, establishing communities in Greenland that persisted for nearly 500 years before disappearing in the 15th century for reasons that historians and archaeologists are still debating. Jump forward 8 or 9 centuries and the sea is still being crossed, still taking vessels, still operating on the same basic terms. The fishing fleets that worked the waters around Iceland and Greenland from the 19th century onward were doing something structurally similar to the Norse voyagers, even if their ships were larger and their charts were better. They were crossing or working within a sea that had not become more forgiving simply because more time had passed. Icelandic fishing communities lost men to the Irminger Sea and the waters around it regularly enough that the losses became part of the social fabric of those communities. There are towns on Iceland's west coast where the memorial lists in the local churches run to dozens of names, fishermen and sailors taken by the North Atlantic in a stretch of decades. The Faroes were in similar straits. Their fishing vessels worked the waters between the Faroes, Iceland and the Greenland banks, and the route took them through or near the Irminger Sea depending on where the fish were running. Losses were not exceptional events. They were the background condition of the industry. The specific character of the losses is worth noting. These were not always dramatic sinkings in full storm conditions. Some vessels simply failed to return. A boat would leave port, enter the fishing grounds, and not come back. No distress signal, no wreckage found, no clear explanation. The Irminger Sea is large enough and remote enough that a vessel lost in its central basin might leave very little trace. A wooden boat breaking up in heavy seas disperses quickly. The currents carry debris in multiple directions. The water is cold enough to preserve little. What you are left with sometimes is an absence, a ship that was there and then was not. The Great Circle route, the shortest distance between 2 points on a sphere, from northern Europe to the eastern coast of North America, passes directly through or very close to the Irminger Sea. This meant that as transatlantic shipping developed in the 19th century and expanded dramatically in the early 20th, the Irminger Sea was not just a remote fishing ground but a maritime highway. Passenger liners, cargo ships and naval vessels all passed through waters where the Greenland tip jet could accelerate to hurricane force, and the confused seas could overwhelm vessels that were not built to handle cross swells from 3 directions simultaneously. The Danish training ship København is one of the more haunting cases associated with these waters. A 5-masted bark, 131 metres long, built in 1921, it was one of the largest sailing vessels of its era. The København left Buenos Aires in December 1928 with a crew of 60, including a number of young cadets on their first ocean voyage. It was last seen by another vessel near the South Atlantic heading southward, or possibly already turning northward, depending on which account you follow, and then it vanished. No wreckage was ever conclusively identified. No bodies were recovered. The ship simply ceased to exist as a documented presence in the world. The København was in the South Atlantic when it disappeared, not the Irminger Sea itself. But the case is relevant here for a couple of reasons. First, the route the ship would have taken on a return voyage to Denmark would have brought it northward through the South Atlantic around the British Isles, and potentially through waters adjacent to the Irminger region. Second, and more importantly, the case illustrates something that applies direct to the Irminger Sea. Large, well-built vessels crewed by experienced sailors can be lost completely in the North and South Atlantic without leaving enough evidence to explain what happened. The ocean does not always offer an account of itself. What the Irminger Sea has never had, and this is worth pausing on, is a single defining disaster that gave it a public identity the way some other dangerous waters have. The Bermuda Triangle, whatever one thinks of the claims made about it, became culturally famous partly because people attached specific losses to it and built a narrative around them. The Irminger Sea has no equivalent. Its losses are real and documented, but they are spread across centuries and across many different types of vessels and circumstances. There is no single event that crystallized public awareness of it as a dangerous place. It is dangerous in a quieter, more persistent, more distributed way, which is, in some respects, more honest about how dangerous seas actually work. The early transatlantic aviation routes also passed near the Irminger region. The northern route from Newfoundland to Scotland or Ireland, used by many of the pioneer aviators of the 1920s and 1930s, took aircraft over waters that included the Irminger Sea's general vicinity. Charles Lindbergh's 1927 flight from New York to Paris followed a great circle route that took him near southern Greenland and over the Irminger Sea. He described flying low over the water, skimming through fog, navigating by feel as much as by instrument. The conditions he described, low visibility, disorientation, the sense of the ocean pressing close, are recognizable to anyone who has read accounts of surface navigation in the same waters. Through the mid-20th century, as shipping became more mechanized and weather forecasting improved incrementally, the Irminger Sea remained a place where the gap between available information and actual conditions could be dangerously wide. Radar helped with some hazards. Radio communication meant that a ship in distress could call for help rather than simply disappearing. But the sea itself had not changed. The tip jet still formed around Cape Farewell. The barrier winds still poured cold air off the Greenland ice sheet. The confused seas still built when multiple wind systems competed. The rogue wave risk still existed in the convergent zones. Better tools reduced some of the vulnerability, but they did not eliminate the fundamental problem, which was that the Irminger Sea generates conditions that can exceed the capabilities of vessels and crews operating within it. What is perhaps most striking about the full arc of human navigation through the Irminger Sea, from the Norse longships of the 10th century to the steel trawlers of the 20th, is how consistent the basic experience has been. The technology changes, the ships get larger, stronger, better equipped, the charts get more accurate, the weather forecasts get more detailed, and yet the accounts of people who have worked or crossed these waters across very different eras share a common quality. They describe a sea that requires your full attention and does not guarantee that full attention will be enough. They describe conditions that develop faster than you expect. They describe the cold as something that is not just uncomfortable but actively threatening. They describe the isolation, no land visible, help far away, the horizon offering nothing but more water and more weather. The Norse sailor who lost sight of Iceland and had not yet raised the Greenland coast, navigating by memory and instinct through overcast skies, was in a situation that a modern fishing captain riding out a Forsten gale in the central Irminger Basin would recognise in its essential structure, even if the specific details were different. The sea between them is the same sea. The physics are the same physics. The cold is the same cold. This continuity across 1,000 years of navigation is not a comfortable thought. Exactly, but it is an honest one. Human beings have been crossing the Irminger Sea since before they had accurate maps of it, and they have been losing vessels and people to it throughout that entire period. The losses have become less frequent as technology has improved, but they have not stopped. The sea has not been tamed in the way that some other difficult environments have been made more manageable. It has been crossed repeatedly by people who understood the risk and went anyway, because the fish were there or the route was necessary or the destination was worth it. And it will continue to be crossed by fishing vessels and research ships and cargo carriers for as long as the fish are there and the routes matter and the work needs doing. The fishing industry that operates in the Irminger Sea today is a direct continuation of that long history, carried out with better vessels and better equipment, but under conditions that have not fundamentally changed. The men and women working those boats are the latest in a line that extends back to the Norse settlers, and the sea they're working in is the same sea that turned back half of Eric the Red's fleet more than 1,000 years ago. The economics are different. The technology is different. The relationship between the people and the water is, in its essentials, the same, and what that relationship looks like in practice, what it costs and what it demands, is a story that is still being written every time a trawler leaves port and heads south of Cape Farewell into the grey-green basin of the Irminger Sea. The fishing vessels that work the Irminger Sea today are not romantic objects. They are functional, heavy, built for a specific purpose, and they look it. A typical trawler operating in these waters runs somewhere between 50 and 80 metres in length, with a broad beam and a low freeboard, meaning the distance between the waterline and the deck edge is not as generous as you might hope when a wave comes over the side. The hull is steel. The wheelhouse sits high enough to give the captain some view of what is coming, though in the Irminger what is coming can change faster than any view allows for. These are working vessels, not expedition ships. They carry refrigerated holds, trawl winches, net drums, and the accumulated gear of an industry that has been refining its tools for generations. They are built to handle rough conditions because rough conditions are the baseline, not the exception. The fisheries that draw these vessels into the Irminger Sea are substantial. Greenlandic halibut, also called Greenland turbot, a flatfish that lives in cold, deep water, is one of the primary targets. Redfish, specifically a species called Sebastes mentella, is another. These are deep water fish, living at depths between 500 and 1,000 metres in some cases, which means the vessels working for them are trawling in conditions that combine the hazards of the surface with the technical demands of deep-sea gear handling. Shrimp are also taken in the region, though the shrimp fishery has shifted in recent decades as stock distributions change. Fishing fleets from Greenland, Iceland, the Faroe Islands, and various EU member states all hold quota allocations in different parts of the Irminger Sea and the adjacent waters. This is not a small-scale artisanal fishery. It is an industrialised operation involving dozens of vessels, international quota agreements, and the kind of economics that create pressure to stay at sea when the sensible choice might be to head for port. The quota system matters here, because it shapes behaviour in ways that are not always visible from the outside. A vessel has a certain number of days at sea, a certain tonnage it is permitted to land, and a schedule that does not easily accommodate the weather. If a skipper turns back early because conditions look threatening, that decision has a cost, in fuel, in lost fishing time, in the gap between what was caught and what the economics of the voyage require. There is no malice in this. It is simply the structure of a commercial fishery operating in an environment where the weather is frequently hostile. The pressure to keep fishing when conditions are deteriorating is not unique to the Irminger Sea, but the Irminger amplifies the consequences of that pressure because the deterioration can happen so quickly and the sea state can become so severe. What it looks like to work on deck in these conditions is worth describing carefully, because it is easy to read the word dangerous and not really picture what that means in practice. The temperature of the air in winter sits somewhere between -5 and -15 degrees Celsius in the worst periods. The spray coming off the bow is salt water at roughly 2 to 4 degrees, and it freezes on contact with surfaces, on the deck, on the rigging, on the winch housings, and on the protective gear the crew are wearing. Ice accumulation on a vessel is a serious hazard in itself, because it raises the centre of gravity and can affect stability. Crews have to physically break ice off the superstructure and deck equipment during operations, which means working with tools in the cold while the vessel is moving through heavy seas. The deck is wet and often moving unpredictably. The noise level at force 8 or above, which the Irminger reaches regularly, is such that spoken communication is difficult. Hand signals become important. Everyone knows where everyone else is, because a wave coming over the rail can take a person off the deck faster than they can react, and the water temperature means the window for recovery is extremely short. Sleep deprivation is built into the structure of fishing operations. Trawlers work around the clock, with crew rotating through watches, but the rest periods are interrupted by the need to handle gear, process catch, and respond to whatever the sea and the machinery require. After several days at sea in heavy weather, the physical and cognitive effects of accumulated tiredness become significant. Reaction times slow. Judgment becomes less reliable. Small errors accumulate. The industry is aware of this, and regulations around crew rest exist. But the practical reality of working a trawler in the Irminger Sea is that exhaustion is part of the job in a way that would not be acceptable in most other industries. The losses, when they happen, are documented but not always widely reported outside the fishing communities directly affected. The Icelandic vessel Helga Maria is one example that illustrates what can happen when conditions in the Denmark Strait area become extreme. The vessel was lost in 2004 with crew members killed. The Denmark Strait, which forms the northern boundary of the Irminger Sea's operational zone, is where the cold overflow water descends and where the tip, jet and barrier winds are most intense. Vessels working in that area are operating in some of the most demanding conditions in the North Atlantic. The loss of Helga Maria was not an isolated anomaly. It was a point on a curve that extends backward through decades of fishing history in these waters. Icelandic fishing communities have a long and painful familiarity with this curve. The memorial walls in harbours along Iceland's west coast carry the names of fishermen lost at sea, and many of those losses trace back to waters in or near the Irminger Sea. The Greenlandic fishing industry has its own relationship with these losses, shaped by the particular geography of Greenlandic communities. Many of the ports from which Greenlandic vessels operate are small, isolated and deeply dependent on the fishing industry for economic survival. Nuuk, the capital, is the largest settlement, but fishing operations extend to smaller communities along the west and southwest coasts, where Greenlandic halibut and shrimp have historically supported the local economy. When a vessel is lost, the impact on a small community can be severe and lasting. Families lose breadwinners. Crews that have worked together for years are gone. The community's relationship with the sea, which is already complex and intimate in a way that is hard to communicate to people who have never depended on it, becomes layered with another loss that sits alongside all the previous ones. What keeps vessels going out despite all of this is not indifference to the risk. The fishermen and skippers who work the Irminger Sea are not unaware of what the water can do. Most of them have been at sea long enough to have experienced conditions that frightened them, or to have known people who did not come back. The awareness of risk is constant and specific, not abstract. What keeps them going is the combination of economic necessity, professional identity, and a kind of practical relationship with danger that develops over years of working in a demanding environment. You learn what the sea looks like when it is going to get worse. You learn what your vessel can handle and where the margins are. You develop judgment that is calibrated to the specific conditions of the waters you work, and that judgment becomes part of how you understand yourself as a professional. Turning back is sometimes the right decision, and everyone knows it, but the decision carries weight and is not made lightly. The economic pressure is real and it operates at multiple levels. At the level of the individual vessel, there are fuel costs, crew wages, and loan repayments on the boat itself. Modern fishing vessels are expensive, and many are financed with debt that requires regular income to service. At the level of the fishing company, there are quotas to fill, contracts to meet, and the competitive dynamics of a global seafood market. At the level of the community, there is the dependence of local processors, port facilities, and support businesses on a steady flow of catch. None of these pressures are cynical or malicious, but together they create a system in which the incentive to keep fishing in deteriorating conditions is strong, and the incentive to turn back early is weak. Regulatory bodies and vessel owners have worked to address this through improved safety equipment requirements, mandatory survival suit standards, and better communication systems, but the structural pressure remains. Modern safety equipment has genuinely improved survival odds in some scenarios. Immersion suits, the bright orange survival suits that are standard on fishing vessels, can extend survival time in cold water from minutes to several hours depending on conditions. EPIRBs, emergency position indicating radio beacons, activate automatically if a vessel sinks and transmit a distress signal with position data to search and rescue authorities. Life rafts are designed to deploy automatically and provide some shelter from wind and spray. These are meaningful improvements over what was available to fishing crews in earlier decades. But they are all tools that come into play after something has already gone wrong, and in the Irminger Sea, the interval between something going wrong and the situation becoming unsurvivable can be very short. A vessel that capsizes in a confused sea in the central Irminger Basin in winter with no other vessels nearby presents a rescue challenge that even the best equipment cannot always overcome. The fishing fleets operating in the Irminger Sea today also interact with the scientific and regulatory infrastructure that monitors the fisheries they depend on. Stock assessments conducted by organisations like the International Council for the Exploration of the Sea, known as a CES, use data from research surveys conducted in the Irminger Sea to estimate the size and health of fish populations. These surveys involve research vessels going into the same waters under the same conditions, deploying nets and acoustic instruments to measure what is there. The data they collect feeds into the quota-setting process that determines how much each nation's fleet can catch in a given year. It is a system that connects the difficult physical reality of working in the Irminger Sea to the bureaucratic and economic structures of international fisheries management, and it depends on people being willing to go out there and collect the data that makes the whole system function. There is something worth sitting with in the fact that the Irminger Sea, a body of water that is genuinely difficult to survive, that has taken vessels and crews across 1,000 years of navigation, supports a year-round commercial fishery that involves dozens of vessels and thousands of people. The fish are there because the sea's physical conditions, the upwelling, the mixing of warm Atlantic and cold Arctic water, the deep convection that cycles nutrients through the water column, create an environment that is highly productive biologically. The same forces that make the sea dangerous for the people working on its surface make it rich for the fish living beneath it. The Irminger Current bringing warm, salty Atlantic water into the basin, the Denmark Strait overflow driving circulation, the tip jet stirring the surface layer, all of these processes that create hazard also create productivity. The fishermen are there because the fish are there, and the fish are there because of the same physics that makes the fisherman's work so dangerous. It is a relationship that has a certain bleak coherence to it. What is harder to account for in any simple way is the cumulative effect of this environment on the people who work in it over time. Not just the physical risk, but the texture of a working life conducted in these conditions. Years of watchkeeping in heavy weather, years of managing gear in cold spray, years of making judgment calls about when to push on and when to pull back, years of knowing that the sea you are working on has claimed people you knew. That accumulation shapes something, though it is difficult to name precisely. It shows up in the way experienced fishermen talk about the Irminger Sea, not dramatically, not with the kind of performed toughness that sometimes appears in stories about dangerous professions, but with a specific quiet precision. They describe conditions in terms of what the sea was doing, what the vessel was doing, what they decided and why. The language is practical and calibrated, not theatrical. It is the language of people who have learned to take the sea seriously, without letting the seriousness become paralysing, because paralysis in that environment is its own kind of danger. The fishing industry in the Irminger Sea is not a relic of a previous era, something that will gradually be replaced by safer alternatives. The fish are there, the demand for them is real, and the vessels will keep going out. What may change, and is already beginning to change, is the environment itself, the water temperatures, the ice extent, the distribution of the fish stocks, and the storm patterns that the vessels have to navigate. Those changes are coming from forces that no skipper or fishing company controls, and they are adding a new layer of uncertainty to an environment that was already demanding. The sea that the fishing fleets work today is not quite the same sea that the fleets of 50 years ago worked, and the sea 50 years from now may be different again in ways that are not yet fully understood. What that means for the fisheries, and for the people who depend on them, is a question that connects the daily reality of a fishing vessel working in heavy weather south of Cape Farewell to the much larger story of what is happening to the sea and what it is doing to the world. That larger story, the one happening beneath the surface, in the deep water, in the processes that connect the Irminger Sea to the climate of the entire North Atlantic, is where the next part of this account needs to go. The people who study the Irminger Sea professionally, the oceanographers, the climate scientists, the physical geographers who spend careers trying to understand what this body of water is actually doing, will tell you, fairly quickly, that working here is not like working anywhere else, not because they are trying to dramatise their field, but because the practical reality of conducting science in the Irminger Sea is genuinely unlike what research vessels encounter in most other parts of the world ocean. The sea does not accommodate inquiry. It tolerates it briefly between storms, and then it makes the next attempt considerably harder. Research in the Irminger Sea has been ongoing for decades, driven by a recognition that this basin sits at the centre of some of the most consequential oceanographic processes on the planet. The Atlantic meridional overturning circulation, the great conveyor belt of water that moves heat from the tropics toward the poles and drives much of the climate of the North Atlantic and northwestern Europe, depends critically on what happens in this sea and the waters immediately surrounding it. Understanding how that circulation works, how stable it is, and how it might respond to a warming climate requires sustained, detailed measurement from the Irminger Sea itself. There is no way to study it from a distance and get the answers that matter. You have to go there. Research vessels from multiple nations have been doing exactly that for many years. The RRS Discovery, operated by the Natural Environment Research Council in the United Kingdom, has made numerous survey cruises into the Irminger Sea, deploying instruments, recovering data, and conducting the kind of careful, methodical sampling that builds a long-term picture of how the basin is behaving. The German research vessel Meteor, operated by the German Research Foundation, has conducted similar work. NOAA ships working out of American ports have crossed the Irminger on repeated transects. The Woods Hole Oceanographic Institution in Massachusetts, one of the leading centres for deep ocean research in the world, has had scientists involved in Irminger Sea research for decades, and some of the most important findings about this basin's role in global circulation have come from work conducted by researchers affiliated with that institution. What all of these programs share, beyond their scientific goals, is a common experience of the practical difficulty involved. The Irminger Sea does not behave like a laboratory. Conditions change faster than schedules allow for. A survey planned over several weeks can be disrupted repeatedly by weather systems that force the vessel to heave to hold position against the wind and sea, rather than making progress, for days at a time. A ship heaving to in the Irminger in winter is not in danger necessarily, but it is also not collecting data. It is burning fuel, consuming provisions, and using up the finite time that a research cruise has before it must return to port. Every day spent riding out a storm is a day not spent at a sampling station, and sampling stations missed in the Irminger are not easily made up. The next weather window might not come in time. The instrumentation itself suffers. Mooring arrays, networks of anchored instruments suspended at various depths throughout the water column, are one of the primary tools for sustained measurement in the open ocean. A mooring might consist of a heavy anchor on the seafloor, a line running upward through the water column, and a series of instruments attached at different depths, measuring temperature, salinity, pressure, and current velocity continuously over months or years. The data they collect is invaluable precisely because it captures what the ocean is doing when no ship is present, across seasonal cycles and interannual variations that a single cruise cannot capture. But deploying and maintaining moorings in the Irminger Sea is not straightforward. The currents are strong enough and variable enough that moorings experience significant mechanical stress. Lines can part, instruments can be dragged out of position. In some cases, moorings have simply disappeared, torn loose by currents or in shallower areas, struck by fishing gear passing overhead. Recovering a mooring requires the ship to locate the anchor on the seafloor, send an acoustic release signal that frees the mooring from the anchor, and then wait for it to float to the surface and recover it before weather or current carries it away. In calm conditions in a well-behaved sea, this is a manageable operation. In the Irminger, it can take hours of careful manoeuvring, and if conditions deteriorate during the recovery, the situation becomes complicated quickly. The Ocean Observatory's initiative, a large-scale American scientific infrastructure program funded by the National Science Foundation, made a significant commitment to the Irminger Sea when it deployed a mooring array there beginning around 2014. The Irminger Sea Array, as it became known, was designed to provide the kind of continuous, sustained measurement that individual research cruises cannot deliver on their own. The array included multiple moorings positioned across the basin, carrying instruments at multiple depths, measuring the full range of physical parameters needed to track deep water formation and circulation. Surface buoys at the top of each mooring carried meteorological sensors, measuring wind, temperature, humidity and other atmospheric variables above the sea surface, while the instruments below tracked what the ocean was doing in response. Getting those moorings into the water in the first place required careful planning and a willingness to work in conditions that most people would consider genuinely unpleasant. The deployment cruises went out in weather windows, making the most of periods when the sea was manageable, but the Irminger does not offer long windows. Deploying a mooring involves lowering heavy equipment over the side of a moving vessel, managing long lines in a sea that is rarely flat, and positioning everything precisely enough that the instruments end up where the science requires them to be. The crews and scientists doing this work are skilled and experienced, but the environment tests that skill continuously. Maintaining the array over subsequent years brought its own challenges. Annual service cruises to recover instruments, download data, replace batteries, and redeploy equipment became a regular feature of the program. Some of those cruises went smoothly. Others encountered the Irminger in less cooperative moods. There were instrument losses. There were data gaps caused by equipment failures that could not be repaired at sea. One of the persistent frustrations of sustained ocean observation in a place like the Irminger is that the most extreme events, the winter storms, the deep convection events, the most intense wind and wave conditions, are precisely the conditions that are hardest to measure, because they are the conditions most likely to damage or destroy the instruments trying to record them. The sea hides its most important behaviour behind the very conditions that make observation difficult. Despite all of this, the data collected from the Irminger Sea array and from the research cruises that preceded and accompanied it has been genuinely important. The array captured convection events in real time, tracking the process by which cold, dense surface water sinks to great depths in winter. It documented the variability in those events from year to year, some winters producing deep, vigorous convection, others producing relatively shallow overturning. It measured the heat content of the water column across seasons and years, providing a direct record of how the basin is storing and releasing heat. This is not abstract data. It connects directly to questions about how the North Atlantic climate system is changing and what the Irminger Sea's role in that change might be. There is something that takes a moment to fully appreciate about the situation. Some of the most consequential climate data in the world, data that feeds into models used to project future climate, data that informs understanding of one of the most important circulation systems on the planet, is being collected by instruments sitting in the Irminger Sea, exposed to conditions that regularly damage equipment, by crews working on vessels that have to heave to in storms and wait for the weather to allow them to continue. The global significance of the data and the difficult physical reality of collecting it exist simultaneously, and neither diminishes the other. The science is important precisely because the place is important, and the place is important partly because it is so difficult to access and study. There is also the matter of what happens to the people on the research vessels. Scientists working in the Irminger Sea are not commercial fishermen. They are not there year-round. They are not under the same economic pressures, and they have access to support infrastructure that fishing crews often lack. But they are still at sea, in the Irminger Sea, in conditions that do not become safer simply because the purpose is scientific rather than commercial. Research cruise logs from the basin describe days of heavy weather, equipment problems compounded by rough seas, and the particular exhaustion of trying to conduct precise, careful work on a vessel that is moving constantly and unpredictably. Seasickness, which sounds minor, can be genuinely debilitating on a week-long cruise in heavy Irminger weather. Working with heavy instruments on a wet moving deck in near-freezing conditions requires concentration and care that is harder to maintain when you are physically uncomfortable and sleep-deprived. Some research programs have begun to supplement ship-based observation with autonomous platforms, Argo floats, gliders, and other instruments that can operate independently in the water column without requiring a vessel to be present. Argo floats drift with the currents at depth, periodically rising to the surface to transmit data via satellite before descending again. Underwater gliders can be directed to move through the water along programmed paths, collecting profiles of temperature and salinity as they go. These platforms extend the reach of ocean observation into conditions and time periods when ships cannot safely operate, and they have become an increasingly important part of the observational network in the Irminger Sea. But autonomous platforms have their own limitations in this environment. Argo floats can be difficult to track and recover in the Irminger's complex currents. Gliders, which are relatively fragile instruments, are vulnerable to damage from fishing gear, from the strong currents near the basin boundaries, and from the kind of turbulent surface conditions that the Irminger generates in winter. Data transmission from surface buoys can be interrupted by heavy weather, and no autonomous platform can make the judgment calls that a scientist on a ship can make, adjusting the sampling strategy in response to what the instruments are showing, investigating unexpected features, or deciding that conditions have changed enough to require a different approach. Human presence in the field still matters, even as the tools available for remote observation improve. What the accumulated effort of decades of research in the Irminger Sea has produced is a picture of a basin that is more dynamic, more variable, and more central to the functioning of the North Atlantic climate system than was fully understood even a generation ago. The early view, dominant through much of the 20th century, held that the Labrador Sea to the west was the primary site of deep water formation in the subpolar North Atlantic, the place where the densest water was made and where the deep limb of the overturning circulation was primarily driven. The Irminger Sea was recognised as important but was generally seen as secondary. Research conducted from the 1990s onward, and accelerating through the 2000s and 2010s, has substantially revised that picture. Measurements from the basin, including data from the mooring arrays and from research cruises, demonstrated that deep convection in the Irminger Sea is real, significant, and in some years dominant over what is happening simultaneously in the Labrador Sea. The two basins are connected. Water, heat, and salt move between them, but they behave somewhat independently, and the Irminger's contribution to the overall circulation had been underestimated. Understanding that the Irminger Sea is a primary convection site, not just a secondary one, changes how scientists think about the vulnerability of the Atlantic overturning circulation to disruption, and changes which measurements are most critical for tracking its behaviour over time. It is a revision that required sustained effort to establish, against the resistance of both the scientific consensus and the physical environment. The instruments that made this revision possible, the moorings, the floats, the research vessels, the satellite sensors, are all still there, still working, still accumulating data in a sea that continues to resist easy understanding. The gaps in the record are real. There are periods and locations where the data is thin, where storms prevented sampling or equipment failures left holes in the time series. Scientists working with Irminger Sea data learned to work around those gaps, using statistical methods to fill them cautiously, and acknowledging in their publications the limitations that the environment imposed. It is honest science conducted under difficult conditions, and the honesty about what is missing is part of what makes the findings credible. What is perhaps most striking, sitting with all of this at some remove, is the combination of importance and difficulty that defines the Irminger Sea as a place of scientific inquiry. The questions being asked there, about how the ocean circulates, about how heat moves through the system, about how the climate is changing and what the consequences will be, are among the most important questions in Earth science right now. And the place where those questions must be answered is one of the most physically demanding research environments on the planet. A sea that damages instruments, disrupts schedules, and pushes back against the human desire to measure and understand it. The Irminger Sea does not make its secrets easy to find. It makes the finding of them costly, in time, in equipment and in the sustained effort of the people willing to keep going back. That effort continues season after season because the alternative, not knowing what this sea is doing, is not acceptable given what is at stake. The data being collected in the Irminger Sea today will matter to people who will not be born for decades. It will matter because what happens in this basin, in the deep water formation events that the research vessels are working so hard to document and understand, connects directly to the larger question of how this sea is changing and what those changes mean for the world beyond its borders. That question, the question of what is already shifting in the Irminger Sea and what may be coming, is where the account needs to turn next. So let us stay with that question for a moment. The question of what this sea is actually doing, down in the deep, in winter, when the storms are worst and no ship wants to be there. Because the most important thing the Irminger Sea does, the thing that connects it to the rest of the planet in ways that go far beyond fish and weather, happens below the surface, in the cold, in the dark, and it happens quietly enough that for decades scientists missed just how significant it was. The process is called deep convection. It sounds technical, and in some ways it is, but the basic idea is not hard to follow. In winter, the surface of the Irminger Sea loses heat rapidly to the atmosphere above it. The air is cold, the winds are strong, and the water gives up its warmth to that cold air in enormous quantities. As the surface water loses heat, it becomes denser. Cold water is denser than warm water, and as the density of the surface layer increases, it begins to sink. Not slowly, not gently, it overturns. The water column becomes unstable, and the dense surface water descends, mixing downward through the layers below, sometimes reaching depths of 1,000 meters or more before it finds water of equivalent density and stops. This is convection in the oceanographic sense, a vertical overturning of the water column driven by density differences, not by stirring or wind alone. What makes this remarkable is what it accomplishes. When that surface water sinks, it carries with it the gases it absorbed from the atmosphere, including oxygen and carbon dioxide. It pulls those gases down into the deep ocean, where they can remain sequestered for centuries, sometimes longer. The deep water formed in the Irminger Sea is not just cold water sitting at the bottom of a basin. It is water that has taken a piece of the atmosphere with it on the way down, and it is water that feeds into the larger circulation of the Atlantic Ocean, moving slowly southward through the deep layers, eventually spreading through the world ocean over timescales that dwarf anything in human experience. This is one of the primary mechanisms by which the ocean absorbs carbon dioxide from the atmosphere. And it happens, in significant part, right here, in this grey and difficult sea between Greenland and Iceland. For much of the 20th century, as mentioned a moment ago, the scientific understanding was that the Labrador Sea, the body of water sitting to the west of Greenland, between Canada and Greenland's southern tip, was the main engine of deep water formation in the subpolar North Atlantic. The Labrador Sea was well studied, relatively accessible, and showed clear evidence of deep convection in winter. The Irminger Sea was acknowledged as part of the system, but its contribution was thought to be modest, secondary, a supporting actor rather than a lead. That view began to change in the 1990s and accelerated significantly through the 2000s and 2010s as better instrumentation, more sustained observations and more research cruises produced a more detailed picture of what the Irminger Basin was actually doing. What emerged was somewhat surprising. The Irminger Sea was not just participating in deep water formation. In some years it was the dominant site. The convection events there were deep, energetic and volumetrically significant. The basin was not a secondary player. It was, in certain winters, the primary engine. The 2008 convection event is one of the more well-documented examples. That winter, conditions in the Irminger Sea were particularly favourable for deep convection. The surface was cold, the winds were strong, and the water column was preconditioned by the events of previous years in a way that made overturning easier. Measurements from mooring arrays in the basin, combined with data from Argo floats and research cruises, showed convection reaching depths of around 1,000 metres across a significant portion of the basin. Researchers from institutions including Woods Hole Oceanographic Institution in Massachusetts, along with European partners, documented the event in detail. It was not a subtle signal. The water column overturned dramatically, and the deep water formed during that winter was traceable in subsequent measurements, moving through the basin and eventually feeding into the broader circulation. The 2012 event was similarly significant. Again, strong winter cooling, strong winds, the tip jet and barrier wind systems doing what they do, and a water column that responded by overturning. Again, the instrumentation in the basin captured it, though not without gaps caused by the conditions that made the event possible in the first place. Storms that drive convection are also storms that damage equipment and prevent ships from sampling. There is an uncomfortable irony in that. The most scientifically interesting winters in the Irminger Sea are also the winters when it is hardest to be there. The best data and the worst conditions tend to arrive together. What the research has also shown is that the Irminger Sea and the Labrador Sea do not always behave the same way at the same time. In years when convection is deep and vigorous in the Labrador Sea, the Irminger may be less active, and vice versa. The two basins are connected. They exchange water, heat, and salt through the subpolar gyre, but they respond somewhat independently to the atmospheric forcing above them. This means that understanding the total deep water production in the subpolar North Atlantic requires monitoring both basins simultaneously, not just one. And it means that if something disrupts convection in one basin, the other may or may not compensate. There is no guarantee that the system simply shifts its activity from one location to another. The possibility that both could weaken at the same time is real, and it is one of the things that makes the question of what is happening to these convection sites under climate change so important. The convection process also has a direct relationship with something called the Atlantic Meridional Overturning Circulation, or AMOC, a term that has appeared in the scientific literature with increasing frequency and increasing concern over the past 2 decades. AMOC is the large-scale circulation pattern that moves warm, salty surface water northward through the Atlantic, where it releases heat to the atmosphere and cools, becomes dense, and sinks. The sinking, the deep water formation, is what drives the northward flow of warm water at the surface. The two are connected. The sinking in the north pulls water northward at the surface, and the surface water flowing north is what eventually sinks. It is a loop, and the Irminger Sea is one of the places where that loop closes. If the sinking weakens, if deep convection in the Irminger Sea and the Labrador Sea becomes less vigorous, the northward flow of warm surface water also weakens, and if that flow weakens, the consequences are not local. They are felt across the North Atlantic and beyond. Western Europe receives a disproportionate amount of warmth from the ocean because of AMOC. The Gulf Stream, which is part of the larger AMOC system, carries heat northward that keeps average temperatures in places like Britain and Norway significantly warmer than they would otherwise be at those latitudes. A weakening of AMOC would mean less heat delivered to those regions. It would also mean changes to precipitation patterns, to storm tracks, to the seasonal rhythms that agriculture and ecosystems across the region depend on. The connection between Irminger Sea convection and these larger consequences is not abstract. It is mechanistic. What happens in this basin in winter, when the wind blows hard off Greenland and the surface water cools and sinks, feeds directly into the circulation that shapes the climate of an entire ocean basin and the countries around it. That is a significant responsibility for one grey, difficult, largely unvisited sea to carry. And it carries it quietly, without announcement, year after year, whether or not anyone is there to measure it. One thing worth sitting with is the scale of what happens during a deep convection event. When the water column overturns to a depth of 1,000 metres across a significant area of the basin, the volume of water involved is enormous. The heat exchange between the ocean and the atmosphere during these events is measurable in the energy budget of the entire North Atlantic. The carbon pulled downward is measurable in the ocean's capacity to absorb atmospheric carbon dioxide. These are not small processes, they are planetary in scale, and they happen in a sea that most people have never heard of, in conditions that most people would find difficult to imagine. There is something quietly humbling about that. The ocean does not organise its most important work around human convenience or human attention. The Denmark Strait Cataract, that vast underwater waterfall of cold Arctic water, runs continuously, indifferent to whether anyone is watching. The tipjet howls around Cape Farewell whether or not a ship is there to feel it. And the convection events of 2008 and 2012, and the dozens of winters before and since, happened because the physics of cold water and cold air demanded it, not because a research program was ready to capture them. What the scientists who work in this basin have done, over decades of sustained and difficult effort, is build enough of an observational record to begin to see the patterns, to distinguish a vigorous convection year from a weak one, to track how the deep water formed in the Irminger Sea moves through the basin and eventually feeds into the broader circulation, to detect the slow changes that may be accumulating beneath the year-to-year variability. That record is still being built. It is incomplete in ways that matter. But it's far more complete than it was 20 years ago, and the picture it reveals is one of a sea that is doing something genuinely important for the planet, and doing it in conditions that make documentation costly. The question that follows naturally from all of this, and it is not a comfortable question, is what happens to the convection if the conditions that drive it begin to change. The Irminger Sea sits at the edge of Greenland, and Greenland is losing ice. The fresh water running off that ice sheet into the surrounding ocean is measurable, and it is increasing. Fresh water is less dense than salt water. When it enters the surface layer of the Irminger Sea, it makes that layer less dense, less prone to sinking, less likely to convect. It is, in a physical sense, a lid being placed on the process that drives deep water formation. Not a solid lid, not an immediate one, but a gradual one. A slow dilution of the conditions that allow the sea to do its most important work. Whether that dilution is already affecting convection in the Irminger Sea is a question that researchers are actively working on. The observational record is long enough now to begin looking for trends, but short enough that separating a genuine long-term change from the natural variability of the system is genuinely difficult. The Irminger Sea is highly variable from year to year. A single decade of strong convection followed by a decade of weak convection might be natural variability, or it might be the beginning of something more persistent. Distinguishing between the two requires more data, more time, and more careful analysis than is currently available. That uncertainty is itself significant. It means that one of the most important climate processes in the North Atlantic is being monitored in a sea that resists monitoring, with a record that is still too short to be fully confident about what it is showing. What is not uncertain is the physical mechanism. More fresh water means less dense surface water. Less dense surface water means weaker convection. Weaker convection means less deep water formation. Less deep water formation means a weaker overturning circulation. The chain of consequences is clear in principle, even if the timing and magnitude remain uncertain. And the Greenland ice sheet is losing mass, around 280 billion tons per year by recent estimates, a figure that has been accelerating. The fresh water is entering the ocean. The question is how much, how fast, and whether the Irminger Sea's convection is sensitive enough to respond to what is already happening, or whether the system has more resilience than the simple physics suggests. Those are the questions that make the work in this basin feel urgent in a way that goes beyond academic curiosity. The moorings deployed by the Ocean Observatory's initiative, the research cruises conducted by the RRS Discovery and the RV Meteor and the vessels that came before them, the Argo floats drifting through the basin, the satellite sensors measuring sea surface temperature and salinity from above, All of it is aimed, in part, at answering those questions before the answers become obvious in ways that are harder to address. Science in the Irminger Sea is not just documentation, it is, in a real sense, early warning, and so the basin continues to be watched as carefully as conditions allow by instruments that are regularly damaged and people who regularly risk discomfort and worse to be there. The convection events will continue to happen, or they will not, and the record will show which. The deep water will continue to form, or it will slow, and the circulation will respond accordingly. The sea will remain difficult to work in regardless of what the climate does. The tipjet does not care about research priorities, and the confused seas do not make exceptions for important data collection. What changes, potentially, is what the sea is doing beneath the surface, in the deep water that carries the memory of each winter's cold downward, into the dark and southward through the Atlantic. That dimension of the Irminger Sea, the slow, deep, consequential dimension, sits alongside everything else that makes this water hard to survive. The weather, the waves, the cold, the isolation, all of those things bear down on the surface. But beneath the surface, the sea is doing something that matters to the whole planet. And that process is now caught in the same story of change that is reshaping so much of the natural world. What is already changing in the Irminger Sea, and what those changes may bring, is the question that needs to be followed next. The changes that are already visible in the Irminger Sea are not dramatic in the way that a collapsing ice shelf or a flooded coastline is dramatic. They are quieter than that. They show up in data, in long tables of temperature and salinity readings, in the slow drift of trend lines across decades of measurement. But quiet does not mean small. In the Irminger Sea, some of the most consequential changes happening anywhere in the ocean are unfolding in exactly this way, gradually, measurably, and with implications that extend far beyond the basin itself. Sea surface temperatures in the Irminger Sea have been rising. The warming is not uniform across the basin, and it is not linear year to year. There is still substantial variability, still cold years and relatively warmer years, still the enormous seasonal swings that define a high-latitude ocean. But when you look at the longer record, the trend is there. The surface water is warmer than it was several decades ago. For a sea whose ecological and physical character is built around cold, that shift matters even when the numbers involved seem modest. A degree or two of warming at the surface changes the density structure of the water column. It affects the timing and depth of convection. It alters the conditions under which marine life feeds and reproduces. It changes the sea in ways that are not always visible from the surface, but that propagate downward and outward through the system. Sea ice in the Denmark Strait has been declining. The strait between Iceland and Greenland has historically carried seasonal sea ice southward from the Arctic, and that ice has shaped the ecology and the oceanography of the region for as long as the current climate has been in place. The extent of that ice, how far south it reaches, how long it persists into spring, has been shrinking. Some years now see very little ice in areas where it was once reliable. For marine mammals and seabirds that depend on ice edge environments for feeding, this is a direct disruption. For the oceanography, reduced ice cover means more heat exchange between the ocean and the atmosphere in winter, which can actually enhance convection in some circumstances. But it also means a changed surface energy budget, altered evaporation patterns, and a different relationship between the sea and the atmosphere above it. The system is being rewired in ways that are not yet fully understood. The freshwater question is the one that oceanographers return to most often when they talk about the Irminger Sea and climate change, and it is not hard to see why. Greenland's ice sheet is losing mass at a rate that has been accelerating over recent decades. The most recent estimates put the loss at around 280 billion tonnes per year, though that figure varies with the measurement period and the methodology. What is consistent across different analyses is the direction. The ice sheet is shrinking, and the water from that ice is going somewhere. Most of it enters the ocean around Greenland's coastline, into the fjords, along the continental shelf, and eventually into the open waters of the Irminger Sea and the Labrador Sea to the west. Fresh water is less dense than salt water. That single physical fact carries enormous consequences in this part of the ocean. The Irminger Sea's capacity to form deep water depends on its surface water being cold and salty enough to become denser than the water below it and sink. When fresh water is added to the surface layer, it dilutes the salinity, reduces the density, and makes sinking harder. The surface water needs to cool further before it will convect, or it may not convect at all if the freshwater input is large enough. This is not a theoretical concern. There is observational evidence that freshwater anomalies in the subpolar North Atlantic, pulses of low salinity water, sometimes called great salinity anomalies, have already affected deep water formation in the past. The events of the 1970s and 1980s, when unusually fresh surface water moved through the subpolar gyre, are documented in the oceanographic record and are associated with periods of reduced deep convection. What is different now is that the source of fresh water is not a temporary anomaly. It is the ongoing accelerating melt of the Greenland ice sheet, which is not going to stop producing fresh water unless the warming stops first. The relationship between Greenland melt and the Atlantic meridional overturning circulation has been the subject of intense scientific attention, and in 2021 a study published in Nature Climate Change drew considerable attention by suggesting that AMOC may be approaching a tipping point, a threshold beyond which the circulation could weaken substantially and potentially not recover on any timescale relevant to human civilization. The study used statistical methods applied to sea surface temperature patterns to reconstruct the history of AMOC strength over centuries, and its conclusion was that the circulation has been weakening since the mid-20th century, and that the rate of weakening is consistent with approach toward a critical transition. The study was careful about its claims, and its authors were clear about the uncertainties involved. Other researchers have questioned the methodology and the interpretation. The scientific debate around AMOC stability and tipping points is genuine and ongoing, and there's not yet consensus on exactly how close the system may be to a major transition, or even on how to define that transition precisely. What is not seriously debated is that AMOC is important, and that freshwater input from Greenland is a plausible mechanism for weakening it. The physics is well understood. The question is one of magnitude and timing. How much freshwater, over how long a period, would be required to produce a significant and sustained weakening of the overturning circulation, and whether what is currently entering the ocean is approaching that threshold or is still well below it. Those are hard questions to answer because the system has natural variability that is large, because the observational record is relatively short, and because the models used to simulate AMOC behaviour have no limitations in representing the fine-scale processes, including those in the Irminger Sea specifically, that drive deep water formation. What a weakened AMOC would mean for the Irminger Sea itself is worth thinking through carefully, because the consequences would not be uniform and they would not all point in the same direction. AMOC carries warm, salty water northward from the tropics and subtropics into the subpolar North Atlantic. The Irminger Current, which loops around Cape Farewell and runs northward along Greenland's west coast, is part of this system. If AMOC weakens, the heat transport into the Irminger Sea would likely decrease. Paradoxically, this could mean a colder sea surface in the Irminger region, even as global average temperatures continue to rise, a regional cooling effect driven by reduced ocean heat transport rather than reduced atmospheric warming. There is some evidence in climate model simulations that a weakened AMOC produces a cold anomaly in the subpolar North Atlantic, sometimes called the cold blob, and observations in recent decades have shown that this region has warmed more slowly than most of the global ocean, which some researchers interpret as an early signal of reduced AMOC heat transport. A colder Irminger Sea surface, combined with reduced salinity from continued Greenland melt, would create a complicated and somewhat contradictory environment. The colder surface temperatures would enhance the density contrast needed for convection, potentially supporting it. But the lower salinity would work against convection by reducing density. Which effect dominates would depend on the relative magnitudes of the temperature and salinity changes, and that balance would likely shift over time as the system evolves. This is the kind of non-linear, competing effects situation that makes climate projections for the Irminger Sea particularly difficult to make with confidence. The storm tracks that carry weather across the North Atlantic would also shift if AMOC weakened significantly. The position and intensity of the jet stream is partly influenced by the temperature gradient between the tropics and the poles, and a regional cooling in the subpolar North Atlantic would alter that gradient in ways that affect where storms develop and where they travel. For the Irminger Sea, which already sits in one of the stormiest regions on Earth, a shift in storm tracks could mean either more or fewer extreme weather events, depending on exactly how the atmospheric circulation responds. The Greenland tip jet, which forms in response to Greenland's topography, and the temperature contrast between the ice sheet and the surrounding ocean, would itself be affected by changes in sea surface temperature and ice extent. The behaviour of this already poorly understood and difficult to forecast wind system could change in ways that current models are not well equipped to predict. The fisheries that depend on the Irminger Sea are already responding to changes in the basin. Redfish populations, Greenlandic halibut and shrimp, have all shown shifts in distribution and abundance that are at least partly linked to changing ocean conditions. Warmer water and reduced sea ice have opened some areas to species that were not previously present in large numbers, while other species have moved to follow their preferred temperature ranges. The capelin, a small forage fish that is critical to the food web supporting cod, seabirds and marine mammals across the subpolar North Atlantic, has been shifting its distribution northward as waters warm. These changes in the lower levels of the food web propagate upward through the system, affecting the larger species that fishing vessels target. The fishing communities of Greenland and Iceland, which have organised their economies and their cultures around the marine resources of these waters for centuries, are navigating a sea that is becoming less predictable in ways that go beyond the weather. For the fishing vessels themselves, the practical implications of a changing Irminger Sea are not straightforward to predict. If storm tracks shift, the pattern of dangerous weather might change, not necessarily becoming less dangerous, but becoming dangerous in different ways, at different times of year, in different parts of the basin. If sea ice extent continues to decline, some areas that were previously inaccessible for much of the year may become navigable, extending the range of fishing operations but also exposing vessels to conditions they have less experience with. The economics of the fishery would be affected by changes in stock distributions, potentially pushing vessels into deeper water or farther north, where conditions are even more demanding. None of this makes the sea safer. It makes it different, and different in a context where the accumulated knowledge of generations of fishermen, knowledge about where the dangerous weather comes from, where the currents run, how the sea behaves in different seasons, may become less reliable as a guide. The research community working in the Irminger Sea is acutely aware of all of this, and the urgency of maintaining the observational record has only increased as the evidence of change has accumulated. The mooring arrays, the research cruises, the Argo floats, the satellite observations, all of it is aimed at tracking a system that is in motion, trying to document the changes clearly enough to understand them before they become irreversible. The difficulty is that the Irminger Sea does not become easier to observe as it changes. The storms are still there. The currents still tear at moorings. The tip jet still makes flying dangerous and sailing miserable. The instruments still fail in the cold. The sea does not cooperate with the urgency of the questions being asked of it. There is something quietly vertiginous about this situation. The Irminger Sea is one of the most important places on Earth for understanding how the climate is changing and what those changes will mean for the ocean circulation that distributes heat across the planet. It is also one of the hardest places on Earth to be, to work in, and to monitor. The data that is most needed is being gathered under conditions that make gathering it genuinely difficult and sometimes dangerous. The scientists who deploy the moorings and sail the research cruises and analyse the data are are doing work that matters in a way that is easy to describe abstractly and hard to fully appreciate without understanding what the conditions in that basin actually feel like. The physical reality of the Irminger Sea, the cold, the wind, the waves, the isolation, is not separate from the scientific story. It is part of it. The difficulty of being there is the difficulty of knowing what is happening there, and both of those difficulties matter. What the Irminger Sea is showing in the data that has been gathered at such cost is a system under pressure, not collapsing, not transformed beyond recognition, but changing in measurable ways that are consistent with what the physics predict should happen as freshwater input increases and temperatures rise. The deep convection is still occurring, the overturning circulation is still moving, the fisheries are still productive, the sea is still, in most respects, the sea it has always been. Cold, difficult, consequential, and largely indifferent to human concern. But the trends are there, and the mechanisms that could amplify them are in motion. The Greenland ice sheet will continue to lose mass. The fresh water will continue to enter the ocean. The salinity of the surface layer will continue to be influenced by that input. The convection that drives deep water formation in the Irminger Basin will continue to be watched as carefully as the conditions allow, by instruments that cost enormous effort to maintain, and by researchers who return to this basin year after year despite what it costs them physically to do so. The answers they are looking for will come eventually from the data, from the long, slow accumulation of measurements that will eventually be long enough and complete enough to separate the signal from the noise. What happens in the Irminger Sea does not stay in the Irminger Sea. The deep water formed here moves southward through the Atlantic, carrying with it the memory of each winter's cold and the signature of each year's convection. If that formation weakens, the effects will be felt in the circulation patterns, the heat distribution, and the climate of regions far removed from this grey, windswept basin between Greenland and Iceland. The sea's importance is entirely out of proportion to its fame. Most people have never heard of it. Most people will never see it. But what it does, and what it may stop doing, matters to all of them. That reality, the gap between the Irminger Sea's obscurity and its significance, is part of what makes the human story of this place so worth following. The people who work here, the fishermen and the scientists and the search and rescue crews, are operating in a place that most of the world ignores, doing things that most of the world depends on in ways it does not recognise. And they're doing all of it in conditions that make every other consideration secondary to the simple, immediate problem of surviving the sea. What that survival demands and what it costs is where the story goes next. Search and rescue in the Irminger Sea is not a system that operates under the comfortable assumption that it will arrive in time. The people who run it know better than that. The distances are too large, the weather too variable, the survival windows too narrow. What the system offers is not a guarantee. It is an effort, made under conditions that are sometimes as dangerous for the rescuers as they were for the people they are looking for. The nearest dedicated Coast Guard assets are Icelandic, based primarily in Reykjavik. The United States Coast Guard also maintains operational reach in this region, working from facilities in Iceland and Greenland, and the Icelandic Coast Guard operates fixed-wing surveillance aircraft alongside helicopters. On paper, the coverage sounds reasonable. In practice, the central Irminger Sea sits at a distance that makes response times genuinely alarming. A helicopter flying from Reykjavik to the middle of the Irminger Basin is looking at a transit of somewhere between 6 and 8 hours in each direction, depending on conditions. And conditions in the Irminger rarely cooperate with tight schedules. That is 6 to 8 hours before anyone reaches the position of a vessel in distress. 6 to 8 hours during which the sea continues to do what it does. The survival arithmetic in this basin is unforgiving. Water temperature in the Irminger Sea runs between roughly 2 and 8 degrees Celsius across most of the year, with the colder end of that range being common in winter and in the northern parts of the basin near the Denmark Strait. In 2-degree water, a person without any thermal protection will lose the ability to make useful movements within about 3 minutes. The muscles cool faster than most people expect, particularly in the hands and arms, and the instinct to swim or hold on becomes physically impossible before the mind has fully accepted what is happening. Consciousness can follow within 15 to 30 minutes. In those conditions, the question of whether a rescue helicopter is 6 hours away or 6 minutes away may not change the outcome at all. Immersion suits change that calculation, but only partially. A properly worn survival suit in 2-degree water can extend a person's survival window to somewhere between 1 and 6 hours, depending on the suit's quality, the sea state, the person's size and physical condition, and whether they can keep their head above water. 6 hours sounds like enough time, but only if the distress signal was sent immediately, was received clearly, the position was accurate, the weather allows flight, and the helicopter can actually locate a person in a sea that may be running 4 or 5 meter swells. None of those conditions are guaranteed in the Irminger. In January 2013, a Greenlandic fishing vessel named Polar Nanok went missing in the Denmark Strait area. The vessel had been working in waters north of the Irminger Basin in conditions that were deteriorating. When contact was lost, the search that followed illustrated exactly what search and rescue operations in this region look like in practice. Aircraft were launched from Iceland into weather that was at or near the limits of safe flight. The search area, even with a last known position, expanded rapidly as time passed and currents moved any survivors or debris. The Denmark Strait in winter is not a place where you find things easily. The water is dark, the weather closes in, the swells make visual searching from aircraft extremely difficult, because a person in the water, even in a bright survival suit, disappears in the trough of a wave and may only be visible for a fraction of each wave cycle. The emotional reality of those search operations is something that SAR crews describe with a particular kind of careful language. They are trained to focus on the task, the search pattern, the altitude, the fuel state, the weather window, because focusing on the task is how they stay functional. But underneath the procedure is an awareness that they are flying into conditions that could kill them in order to look for people who may already be beyond help. That awareness does not go away. It sits behind everything. Experienced SAR aircrew in this region describe a kind of disciplined compartmentalization, a learned ability to hold the emotional weight of what they're doing at a slight distance while the work is happening, and then to put it somewhere after the mission is over. How well that works, and for how long, varies from person to person. The helicopters themselves face conditions in the Irminger that push the limits of the aircraft. Icing is a constant concern at the altitudes and temperatures typical of Irminger operations. Ice accumulates on rotor blades, on sensors, on any surface exposed to the air, and it changes the aerodynamics of the aircraft in ways that demand constant attention and management. Visibility can drop to near zero in low cloud and precipitation. Wind speeds in the Greenland tip jet, which can exceed 40 meters per second, are well above the safe operating envelope of most rotary wing aircraft. Crews flying near the tip jet are not flying in it. They're trying to work around it, which requires knowing where it is and where it is moving, which is itself not always easy to determine in real time. Fixed-wing aircraft can cover larger search areas more quickly, but they cannot hover and they cannot rescue. They can locate, they can drop survival equipment, they can relay position information, but the actual extraction of a survivor from the water in the Irminger Sea requires a helicopter and a rescue swimmer willing to enter that water. The rescue swimmer's experience of those conditions, the cold, the wave action, the disorientation of being in a sea that is moving in multiple directions, is something that training can prepare for but cannot fully replicate. The Irminger does not behave like a training pool, or even like a rough training sea. It behaves like itself. Vessels in the area also participate in search and rescue when they can. The maritime tradition of rendering assistance to others in distress is strong in this part of the world, and fishing vessels and merchant ships have been involved in rescues in the Irminger Sea when they were close enough to respond. But a fishing vessel helping a vessel in distress is itself in the same sea, subject to the same conditions, and the act of manoeuvring close to a disabled or sinking vessel in confused seas and strong winds is genuinely dangerous. Crew-to-crew rescues in the North Atlantic are acts of considerable courage dressed up sometimes as simply doing what is expected. The communications infrastructure supporting SAR in the Irminger has improved substantially over the decades. Emergency position indicating radio beacons, EPIRBs, are now standard on commercial fishing vessels and are triggered either manually or automatically on contact with water. The signal goes to satellite, the satellite relays the position to rescue coordination centres, and the response is initiated. In theory, the chain from distress to alert is now very short. In practice, EPIRBs can fail, can be triggered accidentally, can give positions that are imprecise, and can be aboard vessels that sink faster than the beacon deploys. The technology is genuinely good. The sea is genuinely indifferent to how good the technology is. The Icelandic Maritime Rescue Coordination Centre in Reykjavik handles a significant number of incidents in the Irminger region each year. Most are resolved without loss of life. A vessel with mechanical problems, a medical emergency requiring evacuation, a crew member injured on deck. The cases that end badly tend to be the ones that escalate faster than the response can match. A vessel that loses power and control in deteriorating conditions, or one that takes on water faster than the crew can manage, or one that capsizes without warning in a rogue sea. These are the scenarios where the gap between when the alarm is raised and when help arrives becomes the deciding factor. And in the Irminger, that gap is wide. What is perhaps least visible in any account of SAR operations in this region is the cumulative weight that falls on the small communities connected to this sea. Greenlandic and Icelandic fishing communities are not large. The crews who work the Irminger are not strangers to each other. When a vessel is overdue, the people waiting on shore are not waiting for news about an abstract vessel and an anonymous crew. They are waiting for their brother, their husband, their father, their neighbour. The scale of loss in any single incident is small in numerical terms and enormous in human ones. A crew of 7 or 8 people on a fishing vessel represents a significant fraction of the working-age men in some small coastal communities. The loss of a single vessel can change a community for a generation. The SAR crews who respond to these incidents come from those same communities, or from communities like them. The Icelandic Coast Guard, the rescue teams, the helicopter crews. They are not operating at a professional remove from the people they are trying to reach. They know the fishing grounds, they know the vessels, they sometimes know the crews. That proximity is both a motivation and burden, and the people who carry it over many years and many operations carry something that does not show up in any official report. There have been efforts to improve the SAR capacity in the region. Longer-range helicopters, improved satellite communications, better weather forecasting that gives vessels more warning of deteriorating conditions, mandatory safety equipment standards for fishing vessels operating in these waters. These improvements matter. They have saved lives. But the fundamental geometry of the problem has not changed. The Irminger Sea is large, cold, and remote. The weather moves faster than most forecasting systems can track. The survival window in the water is short. The response time from the nearest assets is long. The improvements narrow the gap, but they do not close it. There is also the question of what happens before a distress call is made. The decisions that vessels and their crews make in the hours and days before a situation becomes critical. The economic pressure to stay at sea when conditions are deteriorating is real and persistent. A vessel that turns back early loses fishing time, loses income, and returns to port with a hold that is less full than it could have been. A vessel that stays out and manages the weather successfully is vindicated. A vessel that stays out and does not manage it successfully becomes a SAR case. The line between those two outcomes is not always visible in advance, and the people making the decisions are not operating with perfect information about where the weather is going or how quickly the sea state will worsen. They are making judgment calls under uncertainty, with economic pressure pushing in one direction and risk pushing in the other. The fact that most of those calls turn out to be correct is a testament to the experience and skill of the people making them. The fact that some do not is simply what the Irminger Sea costs. The SAR system in this region represents a serious, sustained commitment to keeping people alive in one of the most demanding maritime environments on Earth. The people who operate it do work that is genuinely difficult and genuinely important, and they do it in conditions that most people will never experience. But it is a system built around the recognition that the sea cannot be made safe, only that its worst outcomes can sometimes, with effort and luck and good timing, be interrupted. What that effort costs the people who make it, not just physically, but in the longer accumulation of difficult missions and hard knowledge about what the Irminger does to the people caught in it, is something that lives mostly in the quiet spaces between official accounts. It lives in the way an experienced SAR pilot describes a winter search in the Denmark Strait area, in the way a rescue coordinator talks about the cases that resolved well and the ones that did not, in the way the fishing communities along the Greenlandic and Icelandic coasts carry the memory of the people they have lost to this water. The sea does not distinguish between the people trying to survive it and the people trying to pull others out of it. It applies the same cold and the same wind and the same waves to all of them equally, and that, in a way that is difficult to articulate but easy to feel, is part of what makes working in this basin a particular kind of experience, one that leaves its mark on the people who do it in ways that are harder to measure than a survival time or a response window, but no less real. The physical toll of the Irminger is the part that shows up in statistics. The rest of what it costs is something the people who work here carry with them in a different way entirely, and that is where the story of this sea continues. There is a particular kind of knowledge that accumulates slowly without ceremony over years of working in a place that does not forgive mistakes. It is not the kind of knowledge you can write down in a manual or pass along in a training session. It lives in the body, in the way a fisherman reads the colour of the sky to the southwest at 4 a.m, or in the way an experienced hand knows from the feel of the deck motion that the sea state is changing before any instrument confirms it. People who work the Irminger Sea long enough develop this kind of knowledge. They also develop something else, something quieter and harder to name, that settles into them over time and does not entirely leave. Greenlandic fishermen have described the experience of working these waters in terms that are not dramatic, but are very specific. The isolation is one of the first things they mention. Not the isolation of being alone in a quiet room, but the isolation of being surrounded by an environment that is indifferent to your presence in a way that is felt rather than understood. For days at a stretch, there is no land visible in any direction. The horizon is a circle of grey water meeting grey sky, and within that circle, the vessel is the only human thing. There is something about that particular geometry. A small steel hull, 40 or 50 metres long, surrounded by thousands of square kilometres of open ocean, that registers differently in the mind than any description of it can capture. Several fishermen interviewed in accounts of North Atlantic fishing life have described it as a kind of pressure. Not a dramatic, overwhelming pressure, but a constant low-level awareness of the scale of what surrounds them and the smallness of what they are in relation to it. The noise is something that does not feature prominently in most accounts of the Irminger, but is described consistently by the people who have worked there. At force 8 and above, which is not an unusual condition in this basin, the wind and sea together produce a sound that is not so much loud as it is total. It fills every space. It comes through the hull, through the windows, through the structure of the vessel itself. It is not something you can step away from or turn down. Experienced fishermen describe learning to sleep through it, which takes time and which is never entirely comfortable. The body adjusts to the motion and the sound, but some part of the mind, some older and more fundamental part, does not fully accept the situation as normal. That part stays alert, and staying alert for days on end, even at a low level, is exhausting in a way that ordinary fatigue does not quite describe. The physical exhaustion of working on deck in near-freezing spray is its own category of experience. A fisherman working a trawl in the Irminger in winter is operating in conditions where the spray freezes on the rigging, where the deck is wet and moving, where the air temperature may be several degrees below zero and the wind chill takes it considerably lower. The work itself is demanding, hauling gear, sorting catch, managing lines, and it requires concentration and physical effort at a time when the body is already working hard simply to stay warm. Hypothermia does not only happen to people who fall overboard. It accumulates in people who work long hours in cold, wet conditions without adequate rest, and it affects judgment before it affects the body in ways that are obvious to an outside observer. A fisherman who is mildly cold and tired makes slightly worse decisions than one who is warm and rested. In an environment where decisions have significant consequences, that difference matters. What is perhaps less discussed, but described clearly by people who have spent extended time in this basin, is the way the Irminger works on the mind over a longer time scale. Not in a dramatic, acute way, but in a gradual, persistent way. Some fishermen describe a kind of practiced calm that develops over years, a learned ability to be present in difficult conditions without being overwhelmed by them. This is a real psychological skill, and it is cultivated deliberately in many fishing communities. The older hands model it. It is passed along not through instruction, but through example, through the way an experienced skipper handles a deteriorating situation without raising his voice, through the way a veteran deckhand keeps working steadily when a newer crew member is struggling to manage his anxiety. The calm is not the absence of awareness. It is something built on top of awareness, a way of functioning that acknowledges the danger without being paralysed by it. But other fishermen describe something different, a low-level anxiety that never fully leaves, even ashore, a tendency to wake suddenly in the night, a difficulty being fully relaxed in the weeks between trips. Some describe watching the weather forecast with an attention that their families find excessive, even when they are nowhere near the sea. This is not uniform across everyone who works these waters, and it would be wrong to suggest that all Irminger fishermen carry this kind of weight. Many do not, or at least do not describe it in these terms, but enough do that it is worth taking seriously as a feature of the experience, not an anomaly. The research on occupational stress and mental health in North Atlantic fishing communities is consistent on one point. Commercial fishing, particularly in high latitude and high risk environments, is among the most psychologically demanding occupations that exist. The combination of factors, physical danger, isolation, sleep disruption, economic pressure, irregular schedules, and the persistent background awareness of risk, creates a particular kind of stress that is chronic rather than acute. It does not arrive as a single overwhelming event. It accumulates. And because fishing communities have traditionally had a culture of resilience and understatement, the accumulation is often not acknowledged until it has been building for a long time. Greenlandic fishing communities carry an additional layer of this that is specific to their history and their relationship with the sea. These are communities where the ocean has been both sustenance and threat for generations. The Irminger Sea and the waters around Greenland's coasts are not abstractions. They are the places where fathers and uncles and brothers went and sometimes did not come back. The losses are not ancient history. They are recent enough that most people in these communities can name the vessels and the people who were on them. That kind of accumulated grief, held across generations and refreshed by new losses, is not something that is easily set aside. It is part of the cultural texture of these places, woven into the way people talk about the sea and the way they prepare their children to understand it. There is a phrase that appears in various forms across accounts from Greenlandic and Icelandic fishing communities, something to the effect that the sea takes what it wants and you do not argue with it. This is not fatalism in the way that outsiders sometimes interpret it. It is not passivity or indifference. It is a hard-won recognition that there are limits to human control in this environment, and that accepting those limits is part of what allows people to function within them. The fishermen who work the Irminger are not reckless. They are skilled, experienced, and careful. But they also operate with an awareness that skill and care are necessary but not sufficient, that the sea has its own logic, and that logic does not always accommodate human plans. This kind of acceptance is psychologically complex. It requires holding two things simultaneously: a genuine commitment to managing risk and making good decisions, and a genuine acknowledgement that those efforts may not always be enough. Most people find it difficult to hold both of those things at once. The mind tends to lean toward one or the other, either toward a sense of control that becomes denial, or toward a sense of helplessness that becomes paralysis. The people who work the Irminger over long careers have often found a way to hold both, and that equilibrium, while it serves them practically, is not without its costs. The question of what support exists for the psychological dimension of this work is one that has received more attention in recent years than it once did. Some research vessels now carry dedicated support for crew mental health on extended expeditions, not because the science crews are in the same situation as commercial fishermen, but because the experience of extended time in a demanding and isolated environment has been recognised as something that affects people in ways that matter. The Danish and Icelandic maritime industries have made efforts to improve mental health resources for fishing crews, though the uptake in traditional fishing communities has been uneven. The culture of resilience that makes these communities functional in difficult circumstances also makes it harder for individuals to acknowledge when they are struggling, and the isolation of the work means that the moments when support would be most useful are often the moments when it is least accessible. There is also something worth noting about the specific character of the Irminger as a place, as distinct from other dangerous maritime environments. It is not a place that announces itself dramatically. It does not have the theatrical violence of a tropical cyclone, where the danger is visible and total and then eventually over. The Irminger's difficulty is persistent and cumulative. The storms come and go, but the cold is always there. The isolation is always there. The awareness of the depth of the water beneath the hull and the distance to the nearest shore is always there. People who work in environments with acute dramatic danger sometimes describe a clarity that comes with it, a sharpening of focus that, while frightening, is also in some ways energizing. The Irminger's particular texture is different. It is more like a long, steady weight than a sudden blow. And long, steady weights are their own kind of difficult. What the sea does to the mind, then, is not a single thing. It is different for different people, and it changes over time for the same person. A young fisherman making his first winter trip into the Irminger experiences it differently than a skipper who has worked these waters for 20 years. A scientist on a research vessel, present for weeks rather than a career, experiences it differently again. But across those different experiences, certain things recur: the sense of scale, the noise, the physical demand, the awareness of remoteness, the particular quality of attention that the environment requires, and for many people, something that stays with them afterward, in the way they talk about the sea, in the way they respond to weather, in the way they carry the knowledge of what this place is. The Irminger Sea does not only threaten the body, though it does that thoroughly and without apology. It also makes a claim on the mind, quieter and slower and harder to quantify, but no less real for being harder to measure. The people who understand this best are the ones who have spent the most time there, the fishermen who have worked these waters for decades, the scientists who have returned to the basin year after year, the SAR crews who know the geography of the place from the particular angle of a search pattern at low altitude in deteriorating visibility. They carry a knowledge of the Irminger that is not only technical, it is something more personal than that, something that belongs to the experience of having been in that place in those conditions for long enough that the sea has had time to make its impression, and that impression, the one that the Irminger leaves on the people who work within it, is part of what this sea is. Not just the oceanography, not just the weather, not just the history of losses and near misses, but the quieter internal record of what it costs to be a human being in a place that is genuinely indifferent to human presence. That record is kept in the people who carry it, and it is passed along in the way fishing communities talk about the sea, in the way skippers train younger crews, in the way a family on shore watches the forecast and waits. It is not a record that shows up in any database or any official account, but it is real, and it is part of the full picture of what the Irminger Sea is and what it does. All of which leads, eventually, to a question that is harder to ask than it might appear. What does it mean to know a place like this? Not to study it, not to navigate it, not to survive it, but to know it, in the deeper sense of having spent enough time in its presence that it has become part of how you understand the world. That kind of knowledge is what the people who work the Irminger accumulate over years, and it is what the sea itself seems to demand as the price of working within it. It is a knowledge that includes the physical and the technical and the historical, but also something beyond all of those, something that has to do with the experience of being small in a very large and very cold place and continuing to show up anyway. That is what the Irminger asks of the people who go there, and what it has meant for the sea itself, what role this difficult, remote, psychologically demanding basin plays in the larger story of the planet, is where this account arrives next. So what does the Irminger Sea mean when you try to hold all of it at once? Not any single piece of it, not the oceanography alone, or the weather, or the history of vessels that crossed it and the ones that didn't come back. Not the deep convection events or the mooring arrays or the SAR helicopters flying low over grey water in deteriorating visibility. All of it together. The whole complicated, cold, persistent, scientifically essential, humanly costly thing. It is tempting to reach for a single frame, to say that the Irminger is above all a dangerous place, or above all a climate engine, or above all a graveyard of ships, or above all a frontier of oceanographic research. But none of those frames quite holds it. The Irminger is all of those things at the same time, and the way those things overlap and interact with each other is part of what makes the sea genuinely hard to understand. It is not a place that yields to a single description. It resists that, the way it resists most things. What is true is that the Irminger does some of the most consequential work in the global ocean. The deep convection that happens in this basin, cold surface water growing dense enough to sink, pulling oxygen downward and drawing carbon from the air, feeding the circulation that moves heat around the planet, is not a local phenomenon. It connects to the Gulf Stream, to the climate of Western Europe, to the pace at which the deep ocean breathes. When researchers at Woods Hole and other institutions documented that the Irminger was not merely a secondary convection site, but in certain years, the dominant one, it changed the way the scientific community understood how the Atlantic works. The Labrador Sea had held that position in the models for decades. The Irminger quietly insisted on being recognised as something more than a supporting player. And yet this sea that does such critical work is also a sea that makes that work genuinely hard to study. The mooring arrays get torn loose, the instruments get damaged, research vessels heave to for days while storms pass, losing data windows that cannot be recovered. The OOI array deployed around 2014 was a major achievement, a network of sensors measuring conditions at multiple depths, transmitting data continuously. But maintaining it has required repeated visits under conditions that are never easy and sometimes dangerous. The science community keeps returning because the data matters enormously, and because there is no substitute for being there. There is no way to understand the Irminger from a comfortable distance. That is, in a way, the sea's defining characteristic. It does not allow comfortable distance. Not for the fishermen who work its waters for Greenlandic halibut and redfish and shrimp, who spend weeks on vessels where the deck is wet and cold and moving, and where the margin between a productive trip and a catastrophe can close in a matter of hours. Not for the SAR crews who fly out from Reykjavik into icing conditions and low visibility to search a few hundred square kilometres of open water for someone who may have only minutes left. Not for the scientists who spend weeks on research vessels in conditions that most people would find genuinely alarming, gathering data that the world needs, but that the sea gives up only reluctantly and at considerable cost. And not for the communities on shore, in Nuuk, in Reykjavik, in the small Faroes ports, who have been watching people they love go out into this sea for generations, and who understand in a way that does not require explanation what it means to wait for a vessel to come back. The Irminger has no single famous disaster. That is worth saying plainly, because it shapes how the sea is understood, or rather, how it tends not to be understood. There is no event here that functions the way certain other maritime disasters do. No wreck that carries the weight of cultural memory. No name that most people outside the region would recognise. The losses have been real, and they have been many, but they have accumulated quietly over centuries in a sea that most of the world has never heard of. The Norse who crossed it on the way to Greenland around 985 CE knew it as a passage to be endured. The fishing fleets that worked it through the 19th and 20th centuries knew it as a place where people died, where the weather turned without warning, where the economics of the catch kept vessels at sea past the point where a more cautious calculation would have turned them home. The Icelandic vessel Helga Maria, the Greenlandic fishing boat Polar Nanok. These names are known to the communities that lost them. They are not known to the wider world. The Irminger's history of difficulty is written in smaller letters than some other seas, but it is no less real for that. And that quietness, the absence of a defining catastrophe, the accumulation of losses that never quite coalesced into a single story large enough to travel, is itself part of what the Irminger is. It is a sea that works on people persistently rather than dramatically. The tip-jet winds that exceed 40 metres per second around Cape Farewell, the confused cross seas that make a 6-metre swell more dangerous than a 10-metre regular one, the water temperature that sits between 2 and 8 degrees Celsius and gives an unprotected person in the water a matter of minutes before useful movement is gone. None of these announce themselves with the theatrical force of a tropical storm. They are simply the conditions. They are what the Irminger is, on a day that is not even particularly remarkable by local standards. The climate picture adds another layer to all of this. The Greenland ice sheet is losing mass at around 280 billion tonnes per year. The fresh water entering the Irminger and the surrounding North Atlantic is diluting the surface salinity, making it harder for water to reach the density needed to sink. If convection slows, if the deep water formation that drives AMOC weakens significantly, the consequences will not stay local. Storm tracks will shift. Heat distribution across the North Atlantic will change. The fisheries that currently exist in the Irminger may not exist in the same form. The 2021 Nature Climate Change study suggesting that AMOC may be approaching a tipping point was not a fringe finding. It reflected a growing body of evidence that the circulation system the Irminger helps drive is under a kind of stress that has no clear historical precedent within the period of human civilization. What happens next is genuinely uncertain. The models disagree on the pace and the magnitude, but the direction of change is not in serious dispute. There is something quietly unsettling about the idea that the Irminger Sea, remote, cold, barely known to most of the world, is one of the places where the future of the planet's climate is being decided. Not in a metaphorical sense, literally. The water that sinks in this basin, the circulation it drives, the heat it moves from the tropics toward the poles, these are physical mechanisms that shape temperature and weather across a vast portion of the Earth. And those mechanisms are being altered by changes that are happening right now, at a rate that the sea's own history does not have a template for. The Norse who crossed it 1,000 years ago were crossing a sea that was already old and already difficult. The sea they crossed is still here, but it is not quite the same sea. What remains through all of this is the image of people going out into it anyway, because the fish are there, because the data is needed, because someone is missing and the helicopters have to fly, because the route from Europe to North America still passes through or near these waters and has since the first ships made the crossing. The Irminger has never been a sea that people chose for its comfort or its ease. It has always been a sea that people entered because they needed to, because the thing they were after, whether it was fish or knowledge or a route or a rescue, was on the other side of the crossing. That quality, the quality of being a place you go because you must, not because it is pleasant, is part of what the sea has always been, and it is part of what makes the people who know it well carry a particular kind of knowledge. Not pride, exactly. Something quieter than that. A familiarity with difficulty that does not require explanation, and a respect for the sea that is not romantic but entirely practical. The skipper who has worked the Irminger for 20 winters does not think of it as dramatic. It is simply the place where the work is, and where the work is genuinely hard, and where the margin for error is genuinely small. That is the knowledge the sea gives to the people who spend time in it, and it is not the kind of knowledge you can get any other way. There is a particular image that stays with you once you have spent time thinking about what the Irminger is. A vessel. It could be a research ship, it could be a trawler, it could be either moving south of Cape Farewell in low cloud, the water grey-green and running in swells that come from two directions at once, the horizon invisible, the sky and the sea blurring together into a single grey mass. The vessel is small against all of that. All vessels are small against all of that. But it is moving forward, carefully, watching the weather instruments, watching the water, doing what it came to do. The people on board are cold and tired and competent, and they are paying attention the way you have to pay attention in a place that will not forgive inattention. And then the cloud closes in a little more, and the vessel disappears into it, and there is only the sea. That is the Irminger, not a place that announces its importance. Not a place that makes itself easy to love or easy to understand. A place that does enormous work quietly, in conditions that resist observation, in a part of the world that most people will never see. A place that has been crossed and worked and studied and mourned for over 1,000 years, and that remains, despite all of that, genuinely difficult. Not in a way that is going to change. The physics of the tip jet, the temperature of the water, the depth of the basin, the speed at which the weather can turn. These are not problems to be solved. They are the character of the place. What changes and what is changing now is the larger context around it. The ice melting, the fresh water entering, the circulation shifting. The sea that has always been hard to survive is becoming harder to understand because the systems that govern it are moving in directions that are new, and the data that would tell us where they are going is still being gathered by researchers in difficult conditions on vessels that are themselves small against the scale of the basin. And somewhere in all of that, the science, the history, the weather, the losses, the people who carry the knowledge of this place in their bodies and their memories, is a sea that deserves to be known, not as a curiosity, not as a backdrop, as a place that matters, in ways that are both very old and very urgent, and that asks more of the people who enter it than almost any other body of water on Earth. That asking is what the Irminger has always done. It asked it of Eric the Red sailors in the 10th century, navigating by sun compass through cloud that gave them nothing to work with. It asked it of the Icelandic cod fishermen in January seas 100 years ago. It asks it of the scientists deploying instruments from a heaving deck in a Force 9, and of the SAR crews flying into icing conditions with a search grid and a narrowing window. It asks it still, every day, of the fishing vessels working the Greenlandic halibut grounds in weather that the forecast did not quite predict. The sea does not care whether the asking is answered. It simply continues to be what it is. Cold, deep, consequential, and very far from anywhere that feels safe. And the people who know it best would probably say that is about right. That is the Irminger. That is what it is to be there. And knowing that, even from a distance, is its own kind of knowledge. Smaller than what the sea gives to the people who go out into it, but real enough to carry with you into the quiet of wherever you are tonight. Sleep well, and if the weather holds, so much the better.